So now we are going to discuss the Fourier transform for the special signals. So for some special signals, directly we are going to find the Fourier transform. So these things always you have to keep in your mind. In examinations, they are going to give the signals and they are going to directly ask the Fourier transform. So that is the reason you have to keep in your mind. So the Fourier transform for the some special signals that we are going to study in the rectangle. These things that we are going to study in a very detailed manner. And the first special signal is the rectangular pulse. It is called as a rectangular pulse. And you can see this is the signal f of t with respect to time domain. So this is a rectangular pulse. Its value is equal to a from minus t by 2 to plus t by 2. And its value is equal to 0 for the remaining time period. So for this rectangular pulse, I want to find what is the Fourier transform. The Fourier transform, which is equal to f of omega is equal to a into t into sa of omega into t by 2. So how we got this one is, which is basically is equal to area of this pulse into sa of omega into width by 2. Width by 2. So what is the area? Area of this pulse is nothing but area length into breadth, where the length is t and this length is area a. So a into t is nothing but at. Sa of omega into what is the width? Width of this field is nothing but t by 2. T by 2. So omega into t by 2 is nothing but omega t by 2. So you have to remember this one, which is for a rectangular pulse. For a rectangular pulse, the Fourier transform is equal to area into sa of omega into width by 2. So this one always you have to keep in your mind. So for a rectangular pulse, the Fourier transform is area into sa of omega into width by 2. So area is nothing but a into t and width is nothing but t. So if you substitute these things, then we are going to get at into sa of omega t by 2. So you have to remember only this important thing. So what I am trying to tell you is very simple, that for a rectangular pulse, the Fourier transform is area into sa of omega into width by 2. So finally, for a rectangular pulse, the Fourier transform is equal to area of the pulse into sa of omega into width by 2. So this one always you have to keep in your mind. So in this case, the area is equal to a into t and the width is t. I substitute and simplify. So therefore we got at into sine of sa of omega t by 2. What's the meaning of sa? Sa t is nothing but sine t by t. I've already told you. Sa t is nothing but sa of t is nothing but sine t by t. Sa of anything, it can be anything, any dummy variable. It is nothing but sine of this dummy variable by dummy variable. So here, it can be anything. It can be t, it can be 2t, it can be 3t, it can be 6t, anything. Keep here same thing, keep here same thing. So sa of t is equal to sine t by t. So this bracket indicates that it can be anything. So sine of this value by same value. So this is a thing always you have to keep in your mind. And there is also one more formula. These two formulas always you have to keep in your mind, which is sinc. Sinc of t. Sinc of t is nothing but same thing. Sine pi t by pi t. Right? So same here also. Sinc of any dummy variable. Any dummy variable is nothing but sine into sine, or you can say pi into the dummy variable by pi into the dummy variable. So this is what I am trying to tell you. So you can say sa t is nothing but sine t by t. Sa of any dummy variable is equal to sine of the dummy variable by the dummy variable. And the sinc of t is nothing but sine pi t by pi t. And the sinc of any dummy variable is equal to sine into pi of the dummy variable by pi of that dummy variable. So the bracket dot means dummy variable. Any dummy variable you can keep it here. Same thing we are going to get follow. So sa of t is equal to sine t by t, and sa of dummy variable is equal to sine of dummy variable by dummy variable. And sinc of t is equal to sine pi t by pi t. Sinc of dummy variable is equal to sine of pi into dummy variable by pi into dummy variable. So these two formulas always you have to keep in your mind. So what's the meaning of this one? Sa of omega t by 2 is nothing but simply, if you simplify, let me simplify here. So let me simplify here. If you simplify, what we are going to get? A into t. Sa of any dummy variable is nothing but sine of the dummy variable by that dummy variable. So omega t by 2, here omega t by t, right? So if you simplify, what you are going to get? T cancels, right? Before they simplify, you are going to get 2a by omega. T cancels into sine of omega t by 2. So this is what I am trying to tell you. So if you simplify finally you are going to get 2a by omega into sine of omega t by 2. So this is the Fourier transform for this signal. But you have to remember the standard formula, which is the Fourier transform is equal to area into saw of omega into width by 2. Their area is 80 and the width is t. So you know, I've already told you, saw of dummy variable is equal to sine of dummy variable by the dummy variable. So with the help of that, we can get sine of omega t by 2 by omega t by 2. So here t cancels and the 2 goes upward. We're going to get 2a by omega into sine of omega t by 2. So this is an actual expression that we can get. So these things always you have to keep in your mind. So let's go for the standard curve. The standard curve means the amplitude is equal to 1. Here the width is equal to 2x. So the width is equal to 2x. So how we can write f of t in terms of standard curve? So this f of t I am going to write in terms of standard curve. F of t is equal to a into g 2x t. Where 2x is nothing but width. 2x is nothing but width. This denominator is nothing but width of the signal. And its amplitude is always equal to 1. For standard curve, its amplitude is equal to 1. And its width, we are writing it here down. This 2x is nothing but, simply, this 2x is nothing but, from this, what we can say, this width is nothing but, if you want to make this one in terms of this one, this 2x is nothing but t. So 2x is equal to t. So therefore, f of t, how we are going to write? F of t is equal to a into g 2x t. G 2x t. The 2x is nothing but, it is equal to t. So this is a standard curve. This is a standard curve. So these things always you have to keep in mind. So therefore we can say f of t is equal to a into g 2x of t. There are 2x. So this width and this width should be same. So this 2x is equal to this width. So the 2x is equal to t. So these things always you have to keep in your mind. So therefore finally for a rectangular pulse, the Fourier transform is area into saw of omega into width by t. The area is nothing but et and width is t. So sine of t is equal to sine t by t. And the saw of any dummy variable is equal to sine of the dummy variable by the dummy variable. And sinc of t is equal to sine pi t by pi t. And sinc of any dummy variable is equal to sine into pi of the dummy variable by pi into the dummy variable. So these things always you have to keep in your mind. So what is the standard curve? Is the standard rectangular pulse curve. It is having a width of 2x and its amplitude is always equal to 1. So if you want to write f of t in terms of g of t, so f of t is equal to a into g2x of t. So this width and this width, both widths should be equal. Then only they are going to become same. So therefore, the 2x is nothing but is equal to t. So this is what I am trying to tell you. Now let's go for the another special signal, which is a triangular signal. So this is the f1 of t I am going to assume. So this is the f1 of t I am going to assume. So this is I will let you tell you later. So you can see this is a triangular signal. So its peak value is a. And this is t and this is t. So what is the overall width? 2t. This overall width is 2t. So this is a triangular signal. So for this triangular signal, I want to find what is the Fourier transform. The Fourier transform is this area of this signal into saw of omega into width by 4 whole square. Only for this saw we have to do the square. Area of the signal into saw of omega into width by 4 whole square. Only for saw whole square we have to do. So what is the area here? Half into base into height, half into what is base here? 2t. And what is height here? A. So half into 2t into a is nothing but a or 80. So omega into what is width here? 2t. It is nothing but 2t. So 2t by 4 is nothing but t by 2. So omega t by 2 whole square. Only for this saw we have to do the square. So this is the part that we are going to get. And then what I told you, saw of t is nothing but sine t by t. Saw square is nothing but just the square of this one. Similarly, saw of dummy variable, you know, sine of dummy variable by the dummy variable. If you want to do the square, do the square, that's it. So therefore, saw of t is nothing but sine t by t. If you want to do the square, do the square here. Saw of dummy variable is nothing but sine of dummy variable by the dummy variable. Square means I will also do a square. That's it. That is what we are going to tell you. So what is the formula? Here, area into saw of omega into width by 4 whole square. So this is what I am trying to tell you. So the only thing that you have to remember for a rectangular pulse. So for a rectangular pulse, what is the Fourier transform? I have already told you. F of omega is equal to area into saw of omega into width by 2. For triangular pulse, what is the Fourier transform? For triangular pulse, the Fourier transform is equal to area into sa of omega into width by 4a, by 4. Again, do the sa square here. Sa square from the sa, sa square. That's it. So therefore, these things always you have to keep in mind. So for rectangular pulse, the Fourier transform is equal to area into sa of omega into width by 2. And for triangular pulse, the Fourier transform is f of omega is equal to area into sa of omega into width by 4 whole square. This sa square you have to do. What is sa? Sa of a dummy variable is equal to sine of the dummy variable by the dummy variable. And sink of the dummy variable is equal to sine of pi into the dummy variable by pi into the dummy variable. So these things always you have to keep in your mind. So therefore you can say what is the area of into base 2t, height is a. So we are going a and 2t and 8t, and what is with the 2t? So 2t by 4 is nothing but t by 2 we are going to get. So omega into t by 2 whole square. So if you want to simplify what you are going to get finally, so let me do small simplification. So t a into sine of sa of omega t by 2 is nothing but sine of omega t by 2 by omega t by 2 whole square. Whole square. So you have to be simplify in order to get certain results that you can get it right. So I don't need to further explain. So these things always you have to keep in your mind. So now here you have to remember, which is for gt of t. So for gt of t, what is the Fourier transform? So for gt of t, I want to find what is the Fourier transform. Gt of t is nothing but it is the standard rectangular pulse of width t and height is 1. So what is the area? 1 into 2 is nothing but t. Sa of omega into width is nothing but t by 2. So omega into t by 2. So this is what that we are going to get right. So now what I will do, I will apply the duality principle. So here in place of omega, I will substitute small t. So t into sa of small t into t by 2. What is the Fourier transform? 2 pi into, in place of small t, I am going to replace t by minus omega. So 2 pi into gt of minus omega. So 2 pi into gt of minus omega. So you know, that's a rectangular pulse is basically the even signal. So therefore, gt of minus omega is equal to gt of omega because it is a rectangular pulse, it is symmetric. Therefore, because of that, 2 pi into gt of omega. So now, what I can say, this I want to convert in terms of time domain. So what I am going to get here, so if you simplify, sa of t into t by 2 is nothing but sine of t into t by 2 by t into t by 2. So tt cancels and 2 is going to come upper. So 2 into sine of t into t by 2 by t. That's it. To simplify this one, we are going to get this one. So this is a duality principle I have applied. So this is a duality principle I have applied. So if I draw the graph, what is going to happen? gt of t is nothing but it is a standard rectangular pulse of width t and having a magnitude of unity 1. So gt of t is nothing but it is having a width of t, means this is t by 2 and this is minus t by 2. And it is having a the magnitude of 1. So for this, what is the Fourier transform? So what is the Fourier transform? Just we have discussed, right? So what we have discussed, so this is the gt of t. So this is the gt of t. Then what is 2 pi into gt of omega I want to draw. I want to just draw the graphs, that's it. 2 pi into gt of omega. 2 pi is nothing but it's r is equal to 2 pi. It is having a width of omega. Means here it will be omega by 2 or minus omega by 2. And the Fourier transform. The Fourier transform. So this is omega. So this is t by 2. And this is the t by 2. Because the width is in terms of capital T, right? And the capital T. This is t by 2. And this is the minus t by 2. And here the amplitude is 2 pi. So this is what I am trying to tell you. So this is what I am trying to tell you. So this point always you have to keep in your mind. So therefore, this is t by 2 and this is minus t by 2. So this is the thing always you have to keep in your mind. So therefore, we can say that for gt of t, so gt of t is nothing but it is a single curve. It is having a magnitude of 1 with the time to the width of t. So this is plus t by 2 and minus t by 2 in a time domain. The time domain of t. So now, if you do the Fourier transform of this one, what are you going to get? Area is 1 into t is t. Sa of omega into width is nothing but t. So t by 2. So if I apply duality because of omega, I substitute t. So t into sa of t into t by 2. If I apply the Fourier transform, 2 pi into gt of minus omega. Here I replace t by minus omega and multiply with 2 pi. And you know the rectangular pulse is basically it is a symmetric. So because of that, gt of minus omega is equal to gt of omega because it is an even signal or symmetric signal. So if I draw the graph, then what I am going to get, it's having a magnitude of 2 pi for a width of t, means here plus t by 2 minus t by 2. in the image domain, frequency domain, omega. So this is what I am trying to tell you. So then another important thing is, suppose, so now, see what is a standard thing here, listen carefully. Suppose there is a standard notation. Suppose there is a triangle. So triangle is standard notation. What is a standard rectangular pulse we have studied? So standard triangular pulse is nothing but. So this is a standard triangular pulse, which is having a width of 2t. It's having a width of 2t and a peak of 1. So I have done like this. Triangle of 2t in terms of time domain t. So 2t is nothing but its width is 2t. Its width is 2t and its peak value is 1. So I have done like this. Suppose if you want to write this signal in terms of standard signal, then you have to keep here e into triangle of 2t in terms of t, because the width is 2t and the peak is a. So like this I can write in terms of standard notation. So now triangle of 2t of t has a Fourier transform. What is the Fourier transform? And what I told you, this is a standard triangle signal of peak value 1 with a width of 2t. Then what is the formula? Area into saw of omega into width by 4 whole square, right? So therefore, what is the area? Area is nothing but half into base is 2t, it is 1. So 2t cancels, we are going to get t into saw of omega into width is nothing but 2t. 2t by 4 means we are going to get t by 2 whole square, saw of square. So now, I will apply the duality principle. So in place of omega, I will substitute t here. So t into saw square into t by 2. What is the Fourier transform? In place of small t, I will replace t by minus omega and multiply by 2 pi. So same thing, 2 pi into pi of 2t of minus omega. So you can see this is also even signal or symmetric signal. So because of that, it will become same as it is 2 pi pi of 2t of omega. So basically, I want to draw this graph. So what is the peak value? 2 pi. And it is in terms of omega and the width is 2t. So this is t and this is minus tt. So therefore the width is 2t. So this is the 2 pi into pi of omega 2t. So therefore you can see I have drawn the picture. So this is this curve. So this is this curve and this is this curve. So these things always you have to keep in your mind. So this is this curve that you always have to keep in your mind. So this is a capital T and this is a minus capital T. So the width is 2t, as you can see clearly here. So these things always you have to keep in your mind. So these are the special signals. These special signals I have told you how to figure out the Fourier transform also. So for the rectangular pulse, how to figure out the Fourier transform, I have already told you. Area into saw of omega into width by 2. And for triangular pulse, for the triangular pulse, the Fourier transform is area into saw of omega into width by 4 whole square. Only for saw square, only for saw we have to do the square here. So anything is an extra multiply by 2 f square, that's it. So this is the thing always you have to keep in your mind. And I have already told you what is the thing of saw. Saw is the thing of saw of some dummy variable is equal to sine of that dummy variable by that dummy variable. And sinc of a dummy variable is nothing but sine pi into the dummy variable by pi into the dummy variable. So this one always you have to keep in your mind. So therefore, you have to remember these 4 things. For the rectangular pulse, the Fourier transform is, you can say, area into saw of omega into width by 2. And for triangular pulse, the Fourier transform is area into saw into omega into width by 4 whole square. Only for saw you have to do square. And the saw of dummy variable is equal to sine of dummy variable by the dummy variable. And sinc of the dummy variable is equal to sine pi of the dummy variable by pi that dummy variable. So this is what I am trying to tell you. So this is what I am trying to tell you. So these points always you have to keep in your mind. So these things always you have to keep in your mind. So finally I can say for the rectangular pulse, the Fourier transform is area into saw of omega into width by 2. And for triangular pulse, the Fourier transform is area into saw square of omega into width by 4. And the saw of dummy variable is equal to sine of dummy variable by the dummy variable. And sinc of dummy variable is equal to sine pi of the dummy variable by pi into the dummy variable. So these things always you have to keep in your mind. Now we are going to discuss another concept which is called as a transfer function. So this concept that we are going to listen in a very clear manner. Listen carefully. Suppose there is an LTI system. LTI system is linear time invariant system. So it is going to satisfy the linearity property as well as the time invariant property. So for this LTI system, the impulse response is h of t. If the input is f of t, then what is the output? Output is nothing but y of t is called f of t combination of h of t, as you can see clearly here. So therefore we can say that for this LTI system h of t, for this LTI system, the input response is h of t. So if the input is f of t, the output is f of t convolution of h of t, as you can see clearly here. So now what I can do, see, I am going to do the Fourier transform for each and every signal. So for the f of t, the Fourier transform is f of omega. So it's a complex number, so I can write in the polar form, which is mod of f of omega into e to the power of j at an angle of f of omega, or you can write mod of f of omega at an angle of f of omega also you can write. And for h of t, the Fourier transform is h of omega. It's a complex number, so you can write the magnitude as well as phase angle, which is mod of h of omega into e to the power of j of phase angle of h of omega, or you can write mod of h of omega or the phase angle of h of omega also you can write. Then for y of t, the Fourier transform is y of omega, which it's a complex number, so I can write in the polar form, which is mod of y of omega into e to the power of j of phase angle of y of omega. So you can see clearly, I can write like this. Let me write here, which is mod of f of omega at a phase angle of f of omega, or mod of h of omega at a phase angle of h of omega. Here, mod of y of omega at a phase angle of y of omega. So these things you have to remember. So I already told you that convention in time domain, it will use to multiplication frequency domain. So y of t is equal to f of t convolution of h of t. So therefore, y of omega is equal to f of omega into h of omega. So y of omega, you know this value, so I have substitute mod of y of omega into e to the power of j of mod of y of omega is equal to f of omega, you know, just substitute here, and h of omega also I have substitute. So if you multiply, these mods are going to get multiplied and the phase angles are going to get added. So mod of f of omega into mod of h of omega into e to the power of j of phase angle of the f of omega plus phase angle of h of omega. These two things are going to get added. So now we need to compare the magnitude part and we need to compare the phase angle part. So mod of y of omega is equal to mod of f of omega into mod of h of omega, and the phase angle of y of omega is equal to the phase angle of h of f of omega plus the phase angle of h of omega. So therefore we can say mod of y of omega is equal to mod of h of f of omega into mod of h of omega, and the phase angle of y of omega is equal to the phase angle of f of omega plus the phase angle of h of omega. So therefore you can see h of omega is called as the frequency response, or it is also called as a transfer function. So h of omega is called as the frequency response, or it is also called a transfer function. And mod of h of omega is called as the magnitude response of the LTI system, and the phase angle of h of omega is called as the phase response of the LTI system. So h of omega is called as the transfer function of the frequency response, and mod of h of omega is called as the magnitude response of the LTI system, and the phase angle of h of omega is called as the phase response of the LTI system. So h of omega is basically called as a transfer function of the LTI system or frequency response of the LTI system. Similarly, mod of f of omega is called as the magnitude response of the LTI system, and the phase angle of h of omega is nothing but phase response of LTI system. So this is what I am trying to tell you. So frequency response of LTI system, LTI system, and or transfer function of LTI system. So these things always you have to keep in mind. So therefore h of omega is called as the frequency response of LTI system or transfer function of LTI system, and the magnitude of h of omega is called as the magnitude response of LTI system, and the phase angle of h of omega is called as the phase response of the LTI system. So these things always you have to keep in your mind. So therefore we can say y of t is equal to f of t combination of h of t. So y of omega is equal to f of omega into h of omega. So these things always you have to keep in your mind. So therefore you already told you just what we have tested for the complex the frequency domain is a complex number, so I counted to magnitude as well as the phase. So the overall magnitude of y of omega is equal to magnitude of f of omega into magnitude of h of omega, and the phase angle of y of omega is equal to the phase angle of h of omega, f of omega plus the phase angle of h of omega. So h of omega is called the transfer function of LTI system or the frequency response of LTI system, and the magnitude of h of omega is called the frequency, you can say the magnitude response of the LTI system, and the phase angle of h of omega is the phase response of the LTI system. So this is what I am trying to tell you. Finally, I can say that suppose I have taken some LTI system. This LTI system is having an impulse response h of t. So if the input is f of t, the output is nothing but y of t is equal to f of t convolution of h of t. So if I want to convert into frequency domain, then f of t Fourier transform will become f of omega, and h of t Fourier transform will become h of omega, and y of t Fourier transform will become y of omega. So the conversion time domain, it leads to multiplication in frequency domain. So y of omega is equal to f of omega into h of omega. So basically all the complex numbers, so I convert the magnitude as in phase angle. So therefore we can say the magnitude of y of omega is equal to magnitude of f of omega into magnitude of h of omega. And the phase angle of y of omega is equal to the phase angle of f of omega plus the phase angle of h of omega. So therefore, h of omega is called as the frequency response of the LTI system or the transfer function of the LTI system. And the magnitude of h of omega is called as the magnitude response of the LTI system. And the phase angle of h of omega is called as the phase response of the LTI system. So these things always you have to keep in mind. So finally, h of omega is basically called as the frequency response of the LTI system or the transfer function of the LTI system. And the magnitude of h of omega is called as the magnitude spectrum of the magnitude response of the LTI system. And the phase angle of h of omega is called as the phase response of the LTI system. So these things always you have to keep in mind. So finally, what's the transfer function? H of omega is called as the transfer function. So now the next concept is conditions for the distortionless in the LTI system. So the next concept that we are going to study is the conditions for the distortionless in the LTI system. So what are the conditions for the distortionless in the LTI system that we are going to study in a very detailed manner? So distortion, what is the conditions for distortionless in an LTI system? This concept that we are going to study in very detailed manner. So what are the conditions for distortionless in the LTI system that we are going to study? Suppose I have taken some LTI system. So for this LTI system, the impulse response h of t is equal to a into delta of t minus t naught. And if the input is f of t, then what is the output? Y of t is equal to f of t convolution of h of t. H of t is equal to a delta of t minus t naught. So f of t convolution of a into delta of t minus t naught is nothing but a is going to come outward, and f of t convolution of delta of t minus t naught is equal to f of t minus t naught. So therefore y of t is equal to a into f of t minus t naught. So this is the output that we are going to get here. So what is LTI system? So I want to basically do the Fourier transform for each and every signal. So for f of t, the Fourier transform is f of omega, and for h of t, the Fourier transform is h of omega, and for y of t, the Fourier transform is y of omega. So y of omega, so you can see, so basically, as I've already told you, one important property in the Fourier transform, I already told you, is for f of t, the Fourier transform is f of omega. Then for f of t plus or minus t naught, what is the Fourier transform? I already told you, which is e to the power of plus or minus j omega t naught into f of omega. So this is what I have told you. So based on this, we can say that y of t is equal to a into f of t minus t naught. So y of omega is equal to a into here f of t minus t naught is nothing but minus a plus means a plus minus minus. So a into e to the power of minus j omega t naught into f of omega. So a into e to the power of minus j omega t naught into f of omega. Same thing, right? So a into e to the power of minus j omega t naught into f of omega. So simplified, I've got a into f of omega into e to the power of minus j omega t naught based on this time shifting property formula. This I got even from the Laplace domain also. So you know the Laplace domain formula, in place of s and j is equal to s is equal to j omega. So we are going to different. Then we are going to get the Fourier transform, right? So therefore this is what I have written. So now I want to find what is h of omega. So h of omega is nothing but, basically I already told you. So y of t is nothing but f of t convolution of h of t. F of t convolution of h of t. So convolution time domain, it will lead to multiplication of frequency domain. So y of omega is equal to f of omega into h of omega. Then what is h of omega? H of omega is equal to y of omega by f of omega. So h of omega is equal to y of omega by f of omega. So you know these two things, right? Just take this f of omega downward, and we are going to get a into e to the power of minus j omega t naught. So this is the transfer function for this system, which is a into e to the power of minus j omega naught. So it's a complex number, right? So I can take the magnitude as well as the frequency, the phase angle. So magnitude of h of omega into e to the power of j of phase angle of h of j omega. So what is the magnitude? Magnitude is equal to a, and what is the phase angle? Minus omega t naught. And what is the magnitude is equal to a? You can say the magnitude is equal to a and the phase angle is nothing but minus omega t naught by comparing this one. So I want to draw the plot here. So magnitude spectrum, magnitude of h of omega for all types of omega, reminiscent to presenting its value is always equal to constant. So its value is always equal to constant for all the time, and its value is equal to a. So what is the bandwidth? Bandwidth is nothing but the range is going to cover all the range from reminiscent to presenting. So bandwidth is equal to infinity. And I want to draw the phase angle plot also. So the phase angle plot for all types of omega. If omega is equal to positive, the phase angle is negative. If omega is equal to negative, the phase angle is positive. So minus omega t naught means it is a straight line passing through region, which is having a negative slope, which is having a negative slope. So therefore, this is nothing but we are going to get this is slope here minus t naught. Slope is nothing but here y is equal to mx. Y is equal to mx. So y is equal to mx. What is y here? Phase angle. And x is nothing but omega. So what is slope? Minus t naught. So y is equal to mx. Y is equal to mx. So y means here angle, the phase angle of h of omega, and x is nothing but omega. So slope is minus t naught. So it is a straight line passing through origin. It is having a negative slope. So this is a graph that we are going to get. So therefore we can say I have taken an LTI system basically which is having impulse response h of t is equal to a delta of t minus t naught. The input is f of t, the output is y of t is equal to a into f of t minus t naught. So basically I have figured out the transfer function for this system. Y of omega is equal to, which is equal to so basically the transfer function of the system h of omega is equal to y of omega by f of omega. So I apply the Fourier transform for the signal y of t. So y of omega is equal to a into e to the power of minus j omega equal to f of omega. So y of omega by f of omega is equal to a into e to the power of minus j omega t naught. So the magnitude value is a, and the phase angle is minus omega t naught. So I have drawn the phase spectrum as well as the magnitude spectrum and phase angle spectrum I have got. So for the magnitude spectrum, it is having a constant value a for all the value of frequency. So its bandwidth is equal to infinity. And its phase angle spectrum is a straight line passing through origin, which is having a negative slope. The negative slope of slope is equal to minus t naught. What is the slope here? The slope is equal to minus t naught. So these things always you have to keep in your mind. So therefore, this is the graph that you always have to keep in your mind. Therefore, this is the concept that you always have to keep in your mind. So this is the concept. Always you have to keep in your mind. Now, we will discuss some points regarding the distortionless in the LTI system. So previously, we have learned the concept. So now, we will discuss some important points regarding the distortionless in the LTI systems. Listen carefully. An LTI system, just making scaling and the shifting, will not make any distortion to the input signal. Suppose, if there is an LTI system, if it is making only scaling as well as shifting, this will not cause any distortion to the input signal. Suppose some LTI system is there, it is doing only either scaling or whether it is shifting, then it doesn't going to provide any distortion to the input. So we can say finally, suppose if you take an LTI system, whether it is scaling the input or whether it is shifting the input, so because of that there will be no distortion in the input. So therefore there is no distortion in the output. So therefore we are not making any distortion to the input signal. So output is basically it is a scaling of the input or the shifting of the input. So an LTI system just making scaling as well as shifting will not make any distortion to the input signal. Suppose if there is LTI system, it is only making the scaling as well as shifting. So because of that, there is no distortion to the input signal. So output is nothing but it is a scaled version as well as a shifted version of the input signal. Then what we have got the transfer function, the Fourier transform of the h of t, which is h of omega is equal to, I have already told you, it's a complex number, so it will have the magnitude as well as phase angle. So magnitude of h of omega into e to the power of j of the phase angle of h of omega. So this we got previously a into e to the power of minus j omega t naught. So by comparing, we can say the magnitude part is a and the angle part is minus omega t naught. So magnitude of h of omega is equal to a and the phase angle of h of omega is equal to minus omega t naught. So this is called as the magnitude response of the LTI system, and this is the phase response of the LTI system. So we can say this is the magnitude response of the LTI system and this is the phase response of the LTI system. As you can see clearly, the magnitude response is constant. Its value is equal to a for all type of frequency, and the phase response is nothing but it is a straight line passing to origin with a slope of minus t naught. An LTI system can be called as distortionless system only if the magnitude response is constant and the phase response is linear. So an LTI system can be called as distortionless system only if the magnitude response is constant and the phase response is linear. Same thing. And what I told you, what is the meaning of distortionless? We are not providing any distortion to the input. Means we are not changing the waveform of the system. We can either do scaling as well as shifting. By that, the signal will be same as it is, only it will be scaled version or shifting version. But we are not going to provide any distortion to this. So therefore, we can say that the magnitude spectrum is a constant spectrum, and the phase angle spectrum is a linear spectrum. So a system is said to be called as distortion system only if the magnitude response is constant and the phase response is linear. So an LTI system called as distortion system only if the magnitude response is a constant as well as the phase response is linear. So therefore, we can say an LTI system can be called as distortionless system only if the magnitude response is constant and the phase response is linear. So finally, I can say an LTI system can be called as the distortionless system only if the magnitude response is constant and the phase response is linear. So finally, I can say an LTI system can be called as the distortionless system only if the magnitude response is constant as well as the phase response is linear. So what is the meaning of distortionless? Distortionless means the input waveform, we are not going to distort it. We are going to keep as it is. So we can do either scaling or either we can do the shifting. So by that, the magnitude response is always constant and the phase response is always linear. Then only the system is said to be distortionless. The constant nature of magnitude response of a distortionless transmission LTI system ensures that all the input components are also present at the response exactly as they present at the input. The constant nature of the magnitude response of a distortionless transmission LTI system ensures that all the input components are also present at the response exactly as they present at input. So basically, what is the meaning of constant magnitude response? Constant magnitude response means whatever the frequencies which are present in the input, same frequencies they are also going to present in the output also. So see, what is the meaning of constant magnitude response? Whatever the frequencies that are going to present in the input, same frequencies that are also going to present in the output. So therefore, the constant nature of magnitude response of distortion transmission LTI system ensures that all the input components are also present at the response exactly as they present at input. So the meaning of magnitude response is constant means whatever the input frequencies, all those frequencies are also going to present in the output. The linear nature of the phase response of a distortionless transmission LTI system confirms that all the input frequencies occurring at a given point of time are delayed uniformly by some amount. So we can say the linear nature of the phase response of a distortionless transmission system confirms that all the input frequencies occurring at a given point of time are delayed uniformly by some same amount. So basically here, what's the meaning of linear nature? If the phase angle is linear nature means simply we can say all the frequencies are going to present. What are the frequencies they are going to present in the input? Same frequencies they are going to present in the output, but all these frequencies are delayed by certain amount of time. So all these are going to delay by certain amount of time. So the linear nature of the phase response of a distortionless transmission LTI system confirms that all the input frequencies occurring at a given point of time are delayed uniformly by same amount. So we can say what are the frequencies they are going to present in the input, same frequencies they are going to present even in the output, but these are delayed by certain amount of time. That is T0. So you can see clearly. See, this is suppose input are having a frequency omega1. Output will also have frequency omega1 after a certain amount of time T0. So if the input is having a frequency of omega1, output will also have the frequency omega1, but it is delayed by certain amount of time T0. For all the things, for all the frequencies of input, they are going to even occur in the output, but they are basically delayed by certain amount of time T0. Now, band gap is a group of frequencies. Band is group of frequencies and bandwidth means width of group of frequencies. Listen carefully. Band is a group of frequencies and bandwidth means width of the group of frequencies. So what is the meaning of band? Band is a collection of frequencies. Bandwidth means the width of the group of frequencies. So what is the width of the group of frequencies? So Band means it's a group of frequencies or collection of frequencies, and bandwidth means width of the group of frequencies. So listen carefully. What is the meaning of band? Band is nothing but it's a group of frequencies or collection of frequencies, and a bandwidth means it is a width of the group of frequencies. So what is the width? What is the width? So what is the meaning of band? Band is nothing but it is also called as the group of frequencies or collection of frequencies, whereas the bandwidth is the width of the group of frequencies or collection of or the width of the collection of frequencies. So bandwidth of a system can also be mathematically defined as width of group of frequencies for which the magnitude response of LTI system is not zero. So bandwidth of a system can also be mathematically defined as the width of group of frequencies for which the magnitude response of LTI system is not zero. So bandwidth of a system can also be mathematically defined as the width of group of frequencies for which the magnitude response of LTI system is not zero. So basically, what is the meaning of bandwidth? What is the meaning of bandwidth of a system? It can also be mathematically defined as a width of group of frequencies for which the magnitude response of the LTI system is not zero. So, see, we have to find for what range of frequencies, the magnitude response is not equal to zero. So, we have to find the width of frequencies for which the magnitude response is not equal to zero. That is called as the, say, until the magnitude of the impulse response is not equal to zero, that which is called as the bandwidth. So bandwidth of a system can also be mathematically defined as the width of group of frequencies for which the magnitude response of LTI system is not zero. So see, until not zero is there, right? Until not zero, all those things, frequencies are considered as the bandwidth of a system. Bandwidth of a distortionless LTI system is infinity. So you can see clearly the magnitude response, the magnitude of the frequency, the magnitude of the h of omega is equal to a for all omega. For all omega it is present. So for all omega is present means it is going to cover the range of omega from NSM to plus infinity. So what is the bandwidth? Bandwidth is nothing but it is equal to infinity. So bandwidth of a distortionless LTI system is nothing but infinity because the magnitude of h of omega is equal to a for all omega from NSM to plus infinity. So what is the meaning of bandwidth? The range of frequencies for which the mod of h of omega is not equal to zero. It is not equal to zero for all that type of omega. So bandwidth is nothing but it is equal to infinity. So bandwidth of a distortionless LTI system is infinity. Suppose let me take one example. So this is a low pass filter, this is a high pass filter, this is a band pass filter, and this is a band reject filter. So what is the meaning of low pass filter? This is a we can say the magnitude response of a low pass filter means only low frequencies are passed and not the high frequencies. Only the low frequencies are passed but not the high frequencies. So this is called as low pass filter. And this is the magnitude response, or we can say the magnitude response of the high pass filter. The low frequencies are not passed, only the high frequencies are passed. And this is the magnitude spectrum of the band pass filter. Only a certain range of frequencies are passed, but not the low frequencies, but not the high frequencies. Whereas band reject filter means only certain band of frequencies are not passed, whereas the remaining things are passed. So only certain band of frequencies are not passed, but the remaining frequencies are passed. This is called the band reject filter means this band of frequencies are not passed. That is the reason this is called the band reject filter. So this is a low pass filter, this is a high pass filter, this is a band pass filter, and this is a band reject filter. So low pass filter means only low frequencies are passed, high pass filter means only high frequencies are passed, band pass filter means only certain band of frequencies are passed, and band reject filter means certain band of frequencies are rejected. So these things always you have to keep in mind. The above are the ideal signal Fourier transforms where h of t not equal to 0 for t less than 0 means non-causal system, so physically can't be realized. So listen carefully. The above are the ideal signals Fourier transforms where h of t is not equal to 0 for t less than 0 means non-causal system, so physically can't be realized. So these are basically the ideal high pass filter diagram, ideal low pass filter diagram, ideal high pass filter, and the ideal band pass filter, and ideal band reject filter. These are the ideal graphs. Ideal frequency response graphs. So if you try to get the h of t, these are h of omega, right? So if you try to get the h of t, then you are going to get h of t is nothing but you are going to get the it is not equal to 0 for t less than 0. So we can say non-causal. Non-causal means they are going to depend upon the future input. So physically we can't realize. So physically it can't be realized. So I already told you this is the band. You can see here this is a rectangular pulse. So we can take here A. Then what is the if you want to get the if you try to figure out the h of t, it will have the h of t. So for all these things, h of t is not equal to 0 for t less than 0. So it is a non-causal signal, means the output is going to depend upon the future values of input. So whenever like these non-causal systems, physically we can't realize. Only the causal systems physically we can build. Only the causal systems we can physically build, but not the non-causal systems. But this is a non-causal system, so physically it can't be realized because these are the ideal graphs. The above are the ideal signal Fourier transforms where h of t is not equal to 0 for t less than 0 means non-causal systems, so physically can be realized. I already told you all these are the ideal graphs. So if you try to figure out the impulse response h of t for t less than 0, its value is not equal to 0. So this is the non-causal signal, means the output is going to depend upon the future values of input. So these are the non-causal system. Non-causal systems cannot be built physically. So therefore we cannot build them. These are the ideal. We can't build them. They are the ideal signals Fourier transforms where h of t not equal to 0 for t less than 0 means non-causal system. So physically they can't be realized. So for practical systems having mod of h of omega, we can figure out the bandwidth omega c by. So for practical system having mod of h of omega, we can figure out the bandwidth omega c by the amount of h of omega c is equal to 1 by root 2 times mod of h of omega max. So listen carefully. Suppose for practical systems, how to figure out the bandwidth. Suppose let me take some practical system. It is having the amount of h of omega. And you can see the magnitude spectrum of h of omega. For a practical system, we have figured out the amount of h of omega, and you have drawn the graph. And now you want to find what is the bandwidth omega c. It is nothing but at omega c, its value is equal to 1 by root 2 times the maximum value. So you can see at bandwidth means at this frequency omega c, the magnitude value is equal to 1 by root 2 times the peak value or the maximum value. So that is called as the bandwidth. So therefore we can say, suppose you have taken some practical system. For the practical system, we have figured out the frequency, the magnitude spectrum of h of omega, we have figured out. So you have to find what is the cutoff frequency or the bandwidth you need to figure out. So that is equal to, at that frequency, its magnitude is equal to 1 by root 2 times the peak value of the magnitude response, which is magnitude of h of omega c is equal to 1 by root 2 times the magnitude of h of omega peak value. So 3 dB bandwidth, it is defined as the width of group of frequencies for which magnitude response of a physically possible system varies following condition. So what is the 3 dB bandwidth? Same thing. This bandwidth is also follows a 3 dB bandwidth. This bandwidth is also follows a 3 dB bandwidth. 3 dB bandwidth, it is defined as the width of the group of frequencies for which the magnitude response of a physically possible system varies following condition, which is the magnitude of h of omega c is equal to 1 by root 2 times the magnitude of h of omega, the maximum value. I have already told you what is the meaning of 3 dB bandwidth. 3 dB bandwidth is, I have already told you, is a group of frequencies for which the condition is the magnitude of h of omega c is equal to 1 by root 2 times the magnitude of h of omega maximum value. So I have already told you what is the meaning of bandwidth. At a certain cutoff frequency, the magnitude value is 1 by root 2 times the peak value. That group, all those group of frequencies are called as a 3 dB bandwidth. 3 dB bandwidth of a signal is defined as width of group of frequencies for which the magnitude spectrum of signal having only significant group of frequencies for which it is going to satisfy. So this is for the bandwidth of the system. Suppose 3 dB bandwidth of system. Suppose if you want to find the 3 dB bandwidth of signal, then so this is for the 3 dB bandwidth of system. System means you have to consider the h of omega. Signal is f of omega. So 3 dB bandwidth of signal is defined as the width of group of frequencies for which the magnitude spectrum of signal having only significant group of frequencies for which it satisfies. Magnitude of f of omega c is equal to 1 by root 2 times the magnitude of f of omega max. So basically, this is for the 3 dB. So if you want to find the bandwidth for the system, is you have to use this one. Suppose for a signal, if you want to find what is the 3 dB bandwidth, you have to use this one. So f of omega c is equal to 1 by root 2 times the magnitude of f of omega for maximum. So this is very simple. System is h of omega, signal is f of omega. That's it. So this is a very important thing. So you can define the bandwidth for system as well as the bandwidth for signal also you can define. So we can define the bandwidth for system as well as the signal also. The property is same. So 3 dB bandwidth is nothing but is the total group of the group of collection of frequencies until which the amount of h of omega the amount of h of omega is equal to 1 by root 2 the amount of h of omega maximum value. Similarly for signals also it is same. Suppose if mod of f of omega is always even function, I've already told the magnitude spectrum is always a even value, is a even function. The magnitude spectrum signal is always a even function. So I've already told you what is the energy under the signal. Energy under the signal f of t and energy under the f of omega both are same. See the time normal signal and the Fourier transform signal both will have the same amount of energy. So energy is equal to integration from t is equal to minus to plus t mod of f of t whole square dt, which is equal to 1 by 2 pi integration from omega is equal to minus to plus t mod of f of omega whole square t omega. So this is an even function, right? Mod of f of omega matrix spectrum is an even function. So now it will become 1 by 2 pi into 2 times of omega is equal to 0 to infinity mod of f of omega whole square d omega. So 2 cancels, we are going to get 1 by pi integration from omega is equal to 0 to infinity mod of f of omega whole square d omega. So this is called the Parseval relation, because whatever the energy under the f of t must be equal to energy under the f of omega. So that is what I have given here. So this is called the Parseval's equation, because the Parseval is a person who has given this equation. So under his name, this is called the Parseval's equation. So the next point is percentage energy bandwidth of a signal is defined as width of group of frequencies to be considered in the spectrum of a signal such that considered group of frequencies contribute the required percentage of total energy of signal. So listen carefully. Percentage energy bandwidth a signal is defined as a width of group of frequencies to be considered in the spectrum of signal such that considered group of frequencies contribute the required percentage of total energy of signal. Suppose, say, I want to find only certain range of bandwidth. If you want only certain range of bandwidth, means you have to choose only those type of frequencies that are going to contribute the corresponding energy. So percentage energy bandwidth of a signal is defined as the width of group of frequencies to be considered in the spectrum of signal such that considered group of frequencies contribute required percentage of total energy of signal. Suppose you want only percentage energy bandwidth of a signal. So if you want only the percentage energy bandwidth of a signal, means you have to consider only those frequencies which are going to give the energy which is required out of the total energy. So listen carefully. The percentage energy bandwidth of a signal is defined as the width of group of frequencies to be considered in the spectrum of a signal as that considered group of frequencies contribute the required percentage of total energy of signal. Suppose if you take some signal, it will have lot of frequencies. So if you consider all the frequencies, then only you are going to get the overall energy, right? Overall energy E. But I want to only have certain amount of energy. I want to have only certain amount of energy. If you want certain amount of energy, means you have to consider only those type of frequencies that can contribute that's what amount of energy. So listen carefully. For f of omega, means it will have all the frequencies. So if you consider all the frequencies, then only you are going to get some energy E. But I want to only have a certain amount of energy, means you have to consider only the certain amount of frequencies that can contribute that much amount of energy. That is the meaning of this statement. So if you consider all the frequencies, means you are going to get the overall energy. But if you want to consider, suppose if you want to only have a certain part of energy, then you have to consider only those type of frequencies, only those group of frequencies, so that they can give that much amount of energy. So percentage energy bandwidth of a signal is defined as a width of group of frequencies to be considered in the spectrum of signal such that considered group of frequencies contribute required percentage of total energy of signal. The next point is 3 dB bandwidth of a signal is a particular case of more general definition of bandwidth of signal called as percentage energy bandwidth, and if we particularly evaluate 50% energy bandwidth, we get 3 dB bandwidth of the corresponding signal. So we can say 3 dB bandwidth of a signal is a particular case of more general definition of bandwidth of the signal called as percentage energy bandwidth, and if we particularly evaluate 50% energy bandwidth, we get 3 dB bandwidth of the corresponding signal. Same thing I already told you. See, if you consider all the frequencies in f of omega, we are going to get the overall energy. Suppose if you want to evaluate only 50% of the overall energy. Suppose if you want to evaluate the 50% of the overall energy, then we have to consider only those frequencies which can contribute the 50% of energy. So if you consider those frequencies, that frequency is nothing but bandwidth, which is also called 3 dB bandwidth. So therefore, you can say finally, I can say, suppose you have considered all the frequencies in the f of omega in order to get the overall energy. But I want to consider only those frequencies which can give only half of the total energy or 50% of the total energy. Then we have to group only those frequencies that can contribute the 50% of total energy. So if I group it and if I figure out that group of frequencies is nothing but is equal to 3 dB bandwidth only. So 3 dB bandwidth of a signal is a particular case of more general definition of bandwidth of a signal called as percentage energy bandwidth. And if you particularly evaluate 50% energy bandwidth, we get 3 dB bandwidth of the corresponding signal. Same thing I told you, right? Now, the next point is, for a signal realized by multiplication of two signals, then bandwidth is known to be sum of the bandwidth of two signals individually. So, for a signal realized by multiplication of two signals, then bandwidth is known to be sum of bandwidth of two signals individually. So, what is the meaning of the signal? Suppose if one signal is the multiplication of two other signals, then the signal bandwidth is the summation of the two individual signal bandwidths. So, listen carefully. Suppose y of t is equal to y1 of t into y2 of t. So, y of t is the multiplication of two signals, y1 of t and y2 of t. Then y of t bandwidth is the summation of the individual signal bandwidths, which is y1 of t has the bandwidth bw1 and y2 of t has the bandwidth bw2. So for y of t, the bandwidth is the summation of the individual signal bandwidth. So bw is equal to bw1 plus bw2. So what I am trying to tell you is very simple. Suppose there is some signal. That signal is the multiplication of the two other signals. And the signal bandwidth is the summation of the individual signal bandwidths. So y of t is equal to y1 of t into y2 of t. So y of t bandwidth is nothing but summation of the individual signal bandwidth, which is bw1 plus bw2. So finally I can say, if any signal is a multiplication of the two signals, then the signal bandwidth is the summation of the individual signal bandwidth. So y of t is equal to y1 of t into y2 of t. So bw is equal to bw1 plus bw2, where bw is the bandwidth of the y of t, bw1 is the bandwidth of the y1 of t, bw2 is the bandwidth of the y2 of t. So these things always you have to keep in mind. So now let's go for the other point, which is if y of t is equal to x of t convolution of h of t. So here input is x of t, and for the entire system the input is h of t. So output is y of t. So if you apply the Fourier transform, I want you to only the convolution in time domain will become will become the multiplication in the frequency domain. So y of omega is equal to x of omega into h of omega. Basically, it will have the complex part as well as the basically it's a complex number. So it will have the magnitude of the phase angle. So therefore, the magnitude of y of omega is equal to magnitude of x of omega into magnitude of h of omega. So then there is also one more thing, phase angle. I will tell separately. Phase angle, I don't want, but let me write here. The phase angle of y of omega is equal to the phase angle of x of omega plus the phase angle of h of omega. This way, we don't need, but let me write it here. So now, this point you have to keep in your mind. So now, I want to find what is the energy under the y of the signal I want to figure out. So basically, I want to find what is the energy in the y of the signal. The formula is 1 by 2 pi integration of omega is equal to minus m to plus m mod of y of omega whole square d omega. So, with the help of the frequency domain of y of omega, I want to find the energy in the signal y of t. Then, mod of y of omega, you know, which is mod of x of omega into mod of h of omega. So, x absolute, I have this square. So, a into b whole square is equal to s to b square. So, therefore, 1 by 2 pi integration of omega is equal to minus m to plus m to mod of x of omega whole square into mod of h of omega whole square d omega. So, this is the relation that you have to keep in your mind. Because mod of y of omega is equal to mod of h of omega, x of omega into mod of h of omega. I have substituted here. So a into b whole square is equal to s into b square. So from that we are going to get this relation. This is the one type of relation. So now the next thing is percentage energy bandwidth of a system. It is defined as bandwidth to be considered for a system such that response energy of a system required percentage of the input energy per considered input. percentage energy bandwidth of a system. It is defined as the bandwidth to be constant for a system such that response energy of the system required percentage of the input energy per a constant input. So what is the meaning of percentage energy bandwidth of a system? It is basically defined as the bandwidth to be constant for a system such that the response energy of the system required percentage of the input energy per a constant input. So suppose it will take some system here. Suppose there is a system here. So it will be a system it will take here. Suppose I want only so I want only X percentage energy bandwidth. So suppose I want only X percentage bandwidth of the system. So if I want only X percentage energy bandwidth of the system, it is defined as the bandwidth to be constant for a system such that the response energy of the system required percentage of the input energy of the corresponding input. Suppose what I am trying to tell you is very simple. So let me tell you what is the meaning of this statement. Suppose there is some system. For the system, the input we are going to get and output we are going to get. So I want to find what is the output. So output we are going to get total energy. So I want to find the output energy only certain amount I want to figure out. Only certain amount. That certain amount is nothing but it is a percentage energy bandwidth. So percentage energy bandwidth of a system, it is defined as a bandwidth to be constant for a system such that the response energy of the system required percentage of the energy input energy or a constant input. So let me give you here some idea. In a practical LTI system, bandwidth of mod of H of omega is equal to 3 dB. So basically I already told you, for any practical LTI system, we are going to find the bandwidth. For any LTI system, what's the meaning of bandwidth? So what is the meaning of bandwidth of the system? It's the 3 dB of the amount of H of omega. So therefore, if you take any practical LTI system, the bandwidth of the LTI system is nothing but it is a 3 dB frequency range of the amount of H of omega, or magnetic response of H of omega. So therefore, we can say a practical LTI system, the bandwidth of the system, which is nothing but is equal to 3 dB range of the amount of H of omega. And energy of Y of t is always equal to 50% of energy of F of t. So always the energy of Y of t is always equal to 50% of the Y of t. So 50% is 50 by 100. Again 50 by 100 is nothing but so basically this is 1 by 2, this is 1 by 2. So 1 by 2 into 1 by 2 is nothing but 1 by 4. 1 by 4 is nothing but 25% is equal to 25% energy of F of t. So output energy is always equal to 25% energy of the F of t. So this point always you have to keep in your mind. So the energy of the Y of t is always equal to 25% of the energy of the F of t. So basically what is the meaning of this one? See, F of t will have lot of frequencies. Out of that only 50% only we are going to consider. And H of t is also going to consider only 50%. So because of that, we are going to get 50% of energy of F of t. So F of t also will have lot of frequencies. Out of that, we are going to consider only 50% of energy. Again, system H of omega is also going to consider only the 50%. So because of that, we are going to get 25% energy of the F of t. So by increasing the bandwidth of H of omega, we can increase the energy at output what we require. So by increasing the bandwidth of the H of omega, we can increase the energy at the output what we require. So here basically what we have taken. So by increasing the bandwidth of H of omega, we can increase the energy at the output what we require. So suppose if we are going to increase the bandwidth of the H of omega. So if you are going to increase the bandwidth of H of omega, means more frequencies are going to pass from input to output. More frequencies are passed means more amount of energy also we are going to get. So therefore we can say finally, whenever you are going to increase the bandwidth of the system H of omega, so more frequencies are going to pass from input to output. So because of that, the energy in the output is also going to get increases. So by increasing the bandwidth of the H of omega, so more frequencies are going to pass from input to output. So because of that, the more the energy in the output is also going to get increases. So by increasing the bandwidth of the H of omega, we can increase the energy at the output what we require. So these are the some of the important points regarding the distortion is in the LTI system. So I want you to remember only one few important things I wanted to remember. A system is said to be distortionless. A system is said to be distortionless only the magnitude spectrum is equal to constant and the phase angle spectrum is a linear one. So because of that, what is going to happen? What's the meaning of distortions? The input is going to either get scaled version or input is going to get shifted version, but there is no distortion in the output. So output is basically only the scale version of input or digit version of the input, but it is not going to provide any distortionless. So these things always you have to keep in your mind. And one more important thing is here. You can say, see, ideal systems, I have already told you. For ideal systems, what is the magnitude spectrum I have told you. But ideal systems cannot be realized because if you try to find the impulse response, its value is equal to 0 for t, its value is not equal to 0 for t less than 0. So we can say it is a non-causal signal. So therefore the system is said to be a non-causal system. So because h of t is not equal to 0 for t less than 0, so we can say the system is said to be a non-causal system. So because of that, what is going to happen? It cannot be physically realizable. So the ideal things that we can't realizable. So because of that reason only, we have figured out the 3 dB range. So 3 dB range is nothing but it is a range of frequencies. For that, the cutoff frequency is nothing but 1 by root 2 times the peak value of the h of omega. This is for system. But if you want for signal means magnitude of f of omega is equal to 1 by root 2 times the magnitude of f of omega peak value. So for signal also you can find the bandwidth, and for system also you can find the bandwidth. So system bandwidth we can figure out with the help of h of omega and the mod of h of omega, and for a signal bandwidth also we can figure out with the help of magnitude of f of omega. These things always you have to keep in mind. And one more thing is here, always by increasing the bandwidth of the system, we are going to pass more amount of signals from input to output. So because of that, the output energy is also going to get increases. And I have given different energy in the f of t is always equal to energy in the f of omega is also I have given. So mod of f of omega is equal to mod of the energy in the signal is same in the magnitude in the time domain as well as the frequency domain. I have given the different types of expressions also I have given. Suppose if one signal is the multiplication of two other signals, then this new signal, then the new signal bandwidth is the summation of the individual signal bandwidths. This one also I have already told you. So these things always you have to keep in your mind. And I have already told you, suppose in the given signal, suppose in the output for a given signal, we got the output. If you apply for the system, entire system, so in the output I have got some energy. But I want only the fraction of energy. Of that energy means you have to choose only the fraction of the frequencies. So by considering the bandwidth to be, by decreasing the bandwidth, we can get the energy what we require. Suppose I given an input as x of t, and by h of t, I got the output y of t. So I have got some energy here, but I want only the fraction of the energy. So by decreasing the bandwidth of the LDI system, I can get only those amount of energy. The output I can get. That is by choosing the bandwidth. By choosing the bandwidth, I can get the output. And also, one more thing is, the energy in the output is always equal to 25% of the energy of the f of t. So this is the maximum energy that we can get. So energy in the y of t, maximum it can be up to only 25% of the energy of the input f of t. And practically I have already told you what's the meaning of 3 dB bandwidth. 3 dB bandwidth is nothing but the output energy is the 50% of the input. 3 dB is nothing but it is a 50% of the input. So these point always you have to keep in your mind. Now we are going to discuss the another concept, which is the cross correlation as well as the auto correlation for the energy signals. So we are going to study about the cross correlation as well as the auto correlation for the energy signals. What is the meaning of energy signals? Those signals which have finite energy and zero power, those signals are called as the energy signals. Suppose let me take two signals f of t and g of t. So if we want to find what is the we can say the cross correlation between the f of t and g of t, the formula is r of f comma g of tau is equal to integration from t is equal to minus f t plus f t f of t into g of t minus tau into dt. So this is called as the cross correlation between the f of t as well as the g of t. So r of f comma g of t is nothing but integration from t is equal to minus f t plus f t f of t into g of t minus tau into dt. So this is called as the cross correlation of the f of t and g of t. But I've already told you what is the convolution of f of t and g of t. So f of t convolution of g of t is equal to integration from tau is equal to minus m to plus m t f of tau g of t minus tau into d tau. So this is basically the convolution, and this is the cross correlation. So this is the convolution of f of t and g of t. This is the cross correlation of f of t and g of t. So if you see, do you find any similarity? So if you see, do you find any similarity? So here t is replaced by tau. So here tau is replaced by t, right? Or simply we can say, so tau is replaced by t, right? And one more thing is here, basically, so or you can say tau is replaced by t, and also we can say here g of minus t. So g of minus t means what you are going to get. So replace g of t by g of minus t. Then what you are going to get? So if you do like this, we are going to get g of minus t minus tau. So listen carefully what I am trying to tell you. So if you want to try to find the relation between these two things, what the relation is? R of f comma g of tau is equal to f of t convolution of g of minus t integration substitute replace t by tau, replace t by tau. So this is what we have to keep in your mind. So if you see clearly, what I am going to mention is very simple. See, this is a f of t convolution of g of t. Then what is f of t convolution of g of minus t? So is nothing but wherever t is there, replace t by minus t, that's it. So integration from tau is equal to minus infinity to plus infinity f of tau and g of minus t minus tau into t tau, right? And now replace tau by t, replace tau by t. So replace tau by t, then what you are going to get? Simply we are going to get like this. So integration from t is equal to minus m to plus t f of t g of, so replace t by tau, replace t by tau. So therefore here you are going to get minus tau minus t capital, this is dt. So dt. So this is what I am trying to tell you. So we can say simply, so now you can say replace tau by t. So replace t by tau or tau by t. This is somewhat confusing, right? So if you see clearly, wherever tau is there, I will replace tau by t. Then what I am going to get? Simply integration from t is equal to minus infinity to plus infinity f of t and g of replace t by tau. So replace t by tau, right? So minus tau here, but replace tau by t, tau by t. Then we are going to get minus t d tau means it will become dt. So this is what I am trying to tell you. So therefore you can see clearly. So this is what that you are going to get here. So simply we can say that the cross correlation. So finally the cross correlation of f comma g, tau is nothing but f of t convolution of g of minus t, and here t is replaced by tau. So t is replaced by tau. So wherever t is there, replace t by tau and tau by t. That's it. So to do the vice versa, replace t by tau and tau by t, then we are going to get this thing. So this is what I am trying to tell you. So therefore we can say that f of t convolution of g of t is equal to integration from t is equal to tau is equal to minus plus t f of tau g of t minus tau d tau. So this is the point I am trying to tell you. So therefore this is the point I am trying to tell you. So therefore let me wrap this part. So let me wrap this part so that you can easily able to understand what I am trying to tell. So this is the relation between f of t and g of t regarding the cross correlation, and this is the convolution between the f of t and g of t. So these two relations always you have to keep in your mind. So these two relations always you have to keep in your mind, which is the cross correlation of f of t and g of t is, you can see clearly here, the integration from t is equal to minus m to plus t f of t g of t minus tau dt. Here t is a variable and tau is a fixed value. And f of t convolution of g of t is equal to integration from tau is equal to minus m to plus t f of tau g of t minus tau d tau. So if we want to find the relation between these two things, which is the cross correlation of f of t and g of t is nothing but f of t convolution of g of minus t. So g of minus t, and then wherever t is there, replace t by 2 and tau by t, then we are going to get this expression that we are going to get here. So what is going to happen? Suppose if g of t is an even function, then what is going to happen? So g of minus t is equal to g of t. So g of minus t is equal to g of t in that case. So because of that, what is going to happen? Then in that case, cross correlation, the correlation is equal to convolution, right? If g of t is an even function, then definitely we can say the correlation is equal to the convolution. If g of t is an odd, then correlation is the negative of the convolution. So you can see clearly here. If g of t is an even function, then g of minus t is equal to g of t. So because of that, the correlation is equal to convolution. If g of t is an odd, so g of minus t is equal to minus of g of t. So because of that, the correlation is the negative of the convolution. So this point always you have to keep in your mind. Basically, let me give this proof. Let me give this proof again. So therefore you can easily able to understand. So as I already told you, the cross correlation between f of t and g of t, which is r of f comma g of tau is equal to integration from t is equal to minus 7 to plus 7t f of t into g of t minus tau into dt. So now the conversion between f of t and g of t is integration from tau is equal to minus 7 to plus 7t f of tau into g of t minus tau into d tau. So basically now I will try to find the conversion between f of t and p of t, which is nothing but integration from tau is equal to minus 7 to plus 7t f of tau into p of t minus tau into d tau. So now I am going to assume p of t as nothing but g of minus t. If p of t is equal to g of minus t, then what is p of t minus tau? So replace t by t minus tau. So replace here t by t minus tau. So you are going to get minus t plus tau. Because I have replaced t by t minus tau, then I in place of t I have substitute t minus tau. So minus of t minus tau is nothing but minus t plus tau. So here p of t is nothing but g of minus t. So above the convolution of g of minus t is nothing but integration from tau is equal to minus 7 to plus 20 f of tau into, so p of t minus tau is nothing but g of minus t plus tau. So minus t plus tau into d tau. So what I will do, I will replace now t to tau and tau to t. So replace t to tau and tau to t. So wherever tau is there, I replace tau by t. Tau is there, I replace tau by t. Tau by t and tau by t. Tau by small t. Then I replace t by tau. So t by tau. So therefore, this is the expression that I am going to get here. So therefore, this is nothing but this one, right? So both are same. So therefore, what is the formula here? The cross correlation of f comma g of tau is equal to f of t convolution of the g of minus t, and finally replace t by tau and tau by t. So this is the final formula. So this formula you have to always keep in your mind. So I have basically given a proof also. So therefore, the cross correlation between the f and g is nothing but convolution of f of t and g of minus t, and finally replace t by tau and tau by t. Then we are going to get this one. So same thing I told you. So therefore, the cross correlation between f and g, which is nothing but f of t convolution of g of minus t, and finally replace t by tau and tau by t, then we are going to get this expression. Suppose if g of t is even function, then g of minus t is equal to g of t, then cross correlation is equal to convolution, then correlation is equal to convolution. Suppose if g of t is odd function, then g of minus t is equal to minus of g of t. So take minus common, then we are going to get correlation is equal to minus of convolution. So this is a very easy thing. I don't have to explain. But I want you to remember only one thing, which is the cross correlation of two function is equal to the convolution of f of t and g of minus t, and finally replace t by tau and tau by t. So this is the thing I want you to remember. So now let me go for the other things. See, this is basically the autocorrelation. Autocorrelation means you are doing the same function again. If you are taking two different functions, means it is called as the cross correlation. If you take in two functions and if you do the other thing is called as a cross correlation, the same function is repeating, means it is called as the autocorrelation. So autocorrelation means the same function we are doing with different functions, means it is a cross correlation. The same function we are doing means it is a autocorrelation, and you are doing with different functions means it is a cross correlation. So autocorrelation of f comma f of tau is equal to, so you know the formula, right? In place of g, replace g by f. Same thing, even thing is same. Integration from t is equal to minus 7 to plus 20 f of t into f of t minus tau into dt. Same thing. Integration from t is equal to minus 7 to plus 20 f of t into f of t minus tau into dt. So how I can write in terms of convolution, how can I write, which is replace g by f, that's it. So f of t convolution of f of minus t, and finally replace t by tau and tau by t. So you are going to get this thing, right? So this is a thing you have to, it's a double arrow, not a single arrow, it is a double arrow. Replace t by tau and tau by t. Then only you are going to get the relation that we want. Then what is cross correlation? Just now we have discovered cross correlation of r of f comma g tau is nothing but integration from t is equal to minus infinity f of t into g of t minus tau dt. Just now we have discussed, right? So this is nothing but f of t convolution of g of minus t. Finally replace t by tau and tau by t. So this I have already told you. So this way I have already told you, right? Finally you have to replace t by tau and tau by t. So this one, as I have already told you so many number of times. So these things always you have to keep in mind. So I want to remember only two important things. What's the cross correlation of f comma f of t and g of t, which is equal to integration of t is equal to minus infinity plus infinity f of t g of t minus tau dt. And what's the convolution of f of t and g of t, which is equal to integration of tau is equal to minus infinity plus infinity f of tau g of t minus tau dt d tau. Then if you want to find the relation between these two things, which is very simple, the cross correlation of f comma g of tau is nothing but the convolution of f of t and g of minus t. Finally replace t by tau and tau by t. Both you need to replace, interchange, or you can say interchange. Then we are going to get the expression that we want. So this is the relation between these two things. Autocorrelation means with the same function you are doing. Cross correlation means with a different function. I already told you autocorrelation means if you are doing the same function. Cross correlation means with different functions if you are doing, that is called as the cross correlation. So basically now let's go for the autocorrelation. So you can see it is an even function. So autocorrelation is basically an even function. So RF of minus tau is equal to RF of tau, because this indicates that autocorrelation is an even function. So always the autocorrelation is always an even function. So because of that, plus tau and minus tau always they are equal. So therefore we can say that RF of minus tau is always equal to RFF of plus tau. So this indicates that autocorrelation is an even function. So RF of minus tau is equal to RFF of tau, because this is defined with respect to tau, and t is a variable. In this case, in this autocorrelation cross correlation, tau is a fixed but t is a variable. So this indicates that autocorrelation is a even function. So let me take the autocorrelation. RF of tau is equal to integration from t is equal to minus m to plus m t f of t into f of t minus tau dt. So now I want to find at tau is equal to 0, what is the value? So RF of at tau is equal to 0, I am going to substitute. So if I substitute tau is equal to 0, then f of t is f square of t dt. So integration from t is equal to minus m to plus m t. So this is nothing but energy of the signal f of t. So therefore, if you in the autocorrelation, if you substitute tau is equal to 0, that value is nothing but energy of the signal f of t. So therefore, we can say in the autocorrelation, if you try to find what is the value at tau is equal to 0, that is nothing but energy of the signal f of t. So therefore, this is the point I want you to always remember. So therefore, we can say that the at tau is equal to 0, if you substitute in the autocorrelation, then the autocorrelation value itself is nothing but it is the energy of the signal f of t. Then I want to find what is the Fourier transform of the autocorrelation I want to figure out. So what is the Fourier transform of the autocorrelation I want to figure out? So this is nothing but it is also called as the ESD, energy spectrum density of the f of t. So this is also called as the energy spectrum density of the f of t, or simply we can say mod of f of omega whole square. So this one you have to remember, which is the Fourier transform of the autocorrelation is equal to energy spectrum density of f of t, or it is also called as the mod of f of omega whole square. So this is what I want you to remember. So therefore finally I can say that the Fourier transform of the autocorrelation is equal to energy spectrum density of the f of t, or mod of f of omega whole square. And here, so you can see this RFF of tau is equal to R f of t minus t naught, f of t minus t naught, both are equal. So here, what is the meaning of this one? Either you take f of t and f of t, or f of t minus t naught and f of t minus t naught. If you do the autocorrelation, it is always same. So f of t and f of t, or f of t minus t naught and f of t minus t naught, their autocorrelation equations are same. So therefore, what I am trying to whether you take f of t or f of t minus t naught and f of t minus t naught, their autocorrelation always you are going to get the same value. So both are always equal. So the autocorrelation of f of t and f of t and the autocorrelation of f of t minus t naught and f of t minus t naught, both are all going to give you the same value. And what is going to happen? As limit t tends to infinity, the autocorrelation of function is going to give you 0. So we can say as limit tends to infinity, the autocorrelation of the function f is going to give you the 0 value. So limit t tends to infinity or f comma f of tau is nothing but it is going to give you 0 value. Means it is going to tend to 0. So therefore limit tends to infinity or f of f comma f of tau is nothing but it is going to tend to 0. Then the autocorrelation of f of g and g of f are both not equal. So the cross correlation of f and g of f both are not equal. So they listen carefully. The autocorrelation of f and g and f both are not same. They are different. So the cross correlation of f and g and f both are different. So cross correlation of f and g and cross correlation of g and f both are not same. We can say both are not equal. But how they are going to be equal is the just here substitute plus tau and here substitute minus tau, then both will be equal. So we can say this the cross correlation of f and g and the cross correlation of g and f are equal. Even here it is a plus tau and it is a minus tau. So this is what I am trying to tell you. So therefore this you have to remember. So the cross correlation of the f and g and f are not equal when both are plus tau and plus tau, but they are equal. One is plus tau and the other is minus tau. So listen carefully. The cross correlation of f and g and f both are not equal for plus tau and plus tau, but they are equal for one is plus tau and the other is minus tau. So this is the point always you have to keep in your mind. So the cross correlation of f and g of plus tau is equal to the cross correlation of g comma f at minus tau. So this point always you have to keep in your mind. So now the next formula is, which is the cross correlation of f of t and g of t is nothing but I have already told you the convolution of f of t and the g of minus t, and finally replace t by tau and tau by t as I have already proved, right? As I have already proved. So you have to keep the double arrow. So you have to keep the double arrow here. Now what is going to happen? Suppose if you want to find the Fourier transform for this one. So you know what is the Fourier transform of f of t. So I have already told you the conventional time domain we use to multiplication of frequency domain. So f of t Fourier transform is f of omega, and g of t Fourier transform is g of omega, and g of minus t Fourier transform is I have already told you g of minus omega, as I have already told you, right? G of minus omega. So g of minus omega is nothing but g conjugate of omega, as I have already told you, because g of omega is a complex number. The real part is even and the imaginary part is odd nature. So because of that, what is going to happen? G of minus omega is equal to g of omega conjugate. As I have already told you, g of omega is a complex number. So real part is even nature and the odd part and the imaginary part is odd nature. So because of that, if you substitute g of minus omega, we are going to get g of omega formless conjugate. So therefore f of omega into g conjugate of omega. So this is a Fourier transform of this one. So now for the autocorrelation of f comma f and tau is equal to f of t convolution of f of minus t. Finally replace t by tau and tau by t, as I have already told you so many number of times. So see, basically initially do the convolution and finally replace t by tau and tau by t, as I have already told you, right? So therefore what we are going to get, that expression that we are going to get, right? So if you want to find what is the Fourier, if you want to find what is the if you want to find what is the if you want to find what is the Fourier transform, then f of t Fourier transform is f of omega, and f of t transform is f of omega. So f of minus t for the Fourier transform is f of minus omega. So f of minus omega is f conjugate of omega. I have already told you, because the Fourier transform is a complex number. So it has real number and imaginary. So real part is even nature and imaginary part is odd nature. So because of that, f of minus omega is equal to f conjugate of omega. F of omega into f conjugate of omega is nothing but mod f of omega whole square, which is called as the energy spectral density. See, F of omega, let me assume A plus IB. A plus IB. F of F conjugate omega is A minus IB. So do the multiplication of these two things. A plus IB and A minus IB is equal to A square plus B square. So what is the meaning of this one? Mod of F of omega. What is mod of F of omega? Under root of A square plus B square. With the square of that one, and what you are going to get? Mod of F of omega whole square is equal to A square plus B square. So this is what I am trying to tell you. So therefore, mod of F of omega whole square is called as the energy spectral density, as I already proved you. So therefore, we can say if F of omega is called A plus IB, then F conjugate of omega is called A minus IB. So if we do the multiplication of these two things, we are going to get A square plus B square, which is nothing but mod of F of omega is equal to A square plus B square. So take the square, then we are going to get A square plus B square. It is nothing but we can say F of omega into F conjugate omega is equal to mod of F of omega whole square. So this is called as the energy spectral density. Suppose if F of t is an energy signal, if F of t is an energy signal, ESD pictures energy per frequency. Energy spectral density, what is also called as the energy per frequency, means how much amount of energy is stored per frequency. So I already told you, as F of t is energy signal and ESD is called as the, it tells energy per frequency. So what is the energy present in each frequency? It is going to tell. So ESD is nothing but just now we have discussed, which is mod of F of omega whole square. Mod means the magnitude spectrum of F of omega whole square, or magnitude of F of omega whole square. So see, I have already told you what is the energy in the signal F of t. Either you can get an expression in the time domain or the frequency domain with the help of Parseval's theorem is equal to 1 by 2 pi integration of omega is equal to minus to plus the mod of F of omega whole square d omega. So this one I have already told you, right? So in the time domain or in the frequency domain, either in the time domain or in the frequency domain, you can basically get the energy same. So energy of F of t is nothing but energy is present in F of t is equal to 1 by 2 pi integration of omega is equal to minus to plus the mod of F of omega whole square d omega. So this is nothing but mod of F of omega whole square is called the energy spectral density. So I have replaced this value by energy spectral density. So 1 by 2 pi integration of omega is equal to minus to plus the energy spectral density into d omega. So now let me write the Parseval's equations in a different format. So let me write the Parseval's equation in different format. The energy in the signal F of t and F of omega is same, which is E is equal to integration of t is equal to minus into plus the mod of F of t whole square dt, or we can write in the other fashion, which is 1 by 2 pi integration of omega is equal to minus into plus the mod of F of omega whole square d omega. As the magnitude spectrum is a magnitude frequency spectrum is based on magnitude spectrum is a even function, so because of that it will become 1 by 2 pi in 2 times of integration of omega is equal to 0 to plus the mod of F of omega whole square d omega. 2 will cancel, we are going to get finally 1 by pi integration of omega is equal to 0 to plus the mod of F of omega whole square d omega. So this is nothing but, I already told you what is the meaning energy of the signal. Energy of the signal I want just now we have discussed, it is nothing but the autocorrelation of the function f of t and f of t at tau is equal to 0. Just now we have discussed that. So the autocorrelation of the f of t at tau is equal to 0, we are going to get the energy in the signal. So these are the different formats. But if you want to write in terms of frequency, then omega is equal to t pi f. So d omega is equal to 2 df. So if you substitute simplify 2 to 2 by cancels, we are going to get frequency is equal to minus infinity to plus infinity mod of f of f whole square df, or because the magnitude spectrum is even function, so you can get like this 2 times of f is equal to 0 to plus infinity mod of f whole square df. You can write in different fashion. So these are the different ways of writing. These things I already told you. So all these things always you have to keep in mind. So now we got the different types of expressions. So we can figure out the energy signal f of t in different formats, with the help of autocorrelation also. Now we can find the energy. So all these things always you have to keep in mind. So cross correlation is doing between two different functions. Autocorrelation is between the same functions, Then the next point is, as I've already told you, suppose y of omega is equal to f of omega into h of omega. Then I've already told you magnitude is nothing but magnitude is the multiplication of two magnitude values, because y of omega is a complex number will have the magnitude and phase angle. F of omega will have the magnitude and phase angle. H of omega will have magnitude phase angle. So I want to know the magnitude. So magnitudes are going to get multiplied. So magnitude of y of omega is equal to magnitude of f of omega into magnitude of h of omega. So now I want to find what is the energy present in the y of t signal I want to find. So I want to find what is the energy present in the y of t signal, which is equal to, we can get either in the time domain or in the frequency domain. So I'll go for the frequency domain. 1 by 2 pi integration of omega is equal to minus m to plus 2 mod of y of omega whole square p omega. See, mod of y of omega, you know, mod of f of omega into mod of h of omega. So a into b whole square is equal to a square b square. So by that we are going to get 1 by 2 pi integration of omega is equal to minus m to plus 17 mod of f of omega whole square into mod of h of omega whole square p omega. And you can see this one is called as the energy spectral density of the f of t. So this is called as the energy spectral density of the f of t. Just now we have discussed, right? So 1 by 2 pi into integration of omega is equal to minus m to plus 17. So this is nothing but energy spectral density of f of t into. So this is nothing but energy spectral density of h of t. You can either write energy spectral density of h of t, you can write, or either you can keep as it is mod of h of omega whole square d omega. So I've already told you energy spectral density of f of t is nothing but mod of f of omega whole square. So these are the different things always you have to keep in your mind. So up to now what we have learned about the cross correlation as well as the auto correlation for the energy signals. So finally, let me write some important formulas so that you can easily able to understand. So always remember only one thing. We can say what is the cross correlation of f comma g in terms of tau. So this one you have to remember, which is equation of t is equal to minus infinity to plus infinity f of t into g of t minus tau into dt. This is a cross correlation between f and g. And what is the convolution? F of t, convolution of g of t, formula you know, which is equal to integration of tau is equal to minus infinity to plus infinity f of tau, h of t, sorry, g of t minus tau into d tau. So if you want to find the relation between these two things, the cross correlation of f and g is equal to f of t convolution of g of minus t. Finally, replace t by tau and tau by t. So this I already proved also. I already proved for you. I already proved, right? So finally, we do the convolution between these two things, and finally interchange t by tau and tau by t. Then we are going to get this expression that we are going to get here. So these things that we are going to get here. So now, then this is a relation, right? And I already told you what is the thing, and what I told you that suppose if g of t is an even function, then what is going to happen? G of minus t is equal to g of t. Then in that case, correlation is equal to convolution. Suppose if g of t is an odd function, and g of minus t is equal to minus g of t. So because of that, minus comes here. So we can say correlation is equal to minus of convolution. And what is the auto correlation? Auto correlation is doing same function. So r of f comma f of tau is nothing but simply integration of t is equal to minus infinity to plus infinity f of t and f of t minus tau dt. So this one I am already told you, right? So now what I can say, this I can write like this: f of t convolution of f of minus t, and finally replace t by tau by t. So I've discussed the same thing is auto correlation, different means cross correlation. This one I've already told you, right? So and also one more important point is that which is always you have to keep in your mind, which is this formula you have to remember, which is the auto correlation of r f is nothing but it is an even function. So auto correlation is always an even function. So plus 2 and minus 2 is always same. So auto correlation is basically an even function. So rf of plus 2 is always equal to rf of minus 2 because it is an even function. And also one more thing is basically I have already told you. Yes, suppose if you substitute tau is equal to 0 and this expression you substitute tau is equal to 0, then f of t into f of t is f square of t, and remaining thing is integration of t is equal to minus into to plus of t, f square of dt is nothing but energy of the signal. So r f comma 0. So this is called as the energy of the signal, which is equal to t is equal to minus infinity to plus infinity f square of t dt. So this is the energy is going to present in the signal f of t. And one more thing I want to tell you, which is what is the energy spectral density? Energy spectral density of f of t is nothing but mod of f of omega whole square. And I've already told you the autocorrelation of f of t and f of t and autocorrelation of the f of t minus t naught and the f of t minus t naught is always same. And I've already told you as limit t tends to infinity, as limit 2 tends to infinity, the autocorrelation function is tends to 0. And I've already told you the autocorrelation of f and g are equal to g and f only for plus 2 or minus 2. So therefore, R this one you have to remember. So always you have to keep in mind, which is the the cross correlation of f and g at plus 2 is equal to the autocorrelation of g and f at minus 2. So this one you have to keep in mind. And I have already told you, which is I have told you the different ways of writing the expression of the energy in different formats also. I have already told you, right? What is the different formats of energy? I have already told you E is equal to integration of T is equal to minus into plus into mod of f of t whole square dt, or 1 by 2 pi integration of omega is equal to minus into plus into mod of f of omega whole square d omega, or you can say the RFF of 0, RFF of 0, autocorrelation of 2 is equal to 0. So these are the different ways I already told you. And one more thing is here, what is the energy spectral density of f of t is nothing but mod of f of omega whole square. So these things always you have to keep in your mind. Now we are going to discuss the other concept, which is the cross correlation and the autocorrelation for the power signals. So previously we have learned about the cross correlation and the autocorrelation for energy signals, but here we are going to discuss the cross correlation and the autocorrelation for power signals. Power signal means the signal which have infinite energy and power is equal to finite. I have already told you, if any signal which is having the infinite energy but a constant, or you can say finite power, then those signals are called as the power signals. So now what is the meaning of the cross correlation? Means if you are doing between the two different functions, it is a cross correlation. Autocorrelation means between the same functions, if you do, then it is called as the autocorrelation. So these things now we are going to discuss in a detailed manner. Suppose for aperiodic signals, aperiodic signal means these are not periodic signals, but still they are power signals. See, basically, so I am taking some non-periodic signals. These are basically power signals also. So I have already told you all the periodic signals are power signals. All the periodic signals are power signals. So some aperiodic signals are also power signals. So for that we are going to discuss. So let me take some for the aperiodic signals. So therefore, the cross correlation of the two different functions f and g, which is equal to limit t tends to infinity 1 by t integration over the one time period f of t into g of t minus tau dt. So if you see clearly what is the difference between the previous thing and here, there we are doing from t is equal to minus m to plus infinity, that we have did there. But here the extra factor is here. We are doing over only one time period and by 1 by t and limit t tends to infinity. So this is the thing you have to keep in your mind. So the extra factor is 1 by t and this limit. And there we did the integration only from minus f to plus infinity, but here from minus t by 2 to t by 2. So this is the point we have to remember. So this is a cross correlation. So this is a cross correlation between the two functions f of t and g of t, which is r f comma g of tau is equal to limit t tends to infinity 1 by t interest over the one time period, which is minus t by 2 to plus t by 2 f of t into g of t minus tau dt. So basically aperiodic signals doesn't have any period, but still we have to take this one. So now for periodic signals with the same time period, suppose I am going to take two periodic signals. F of t is a periodic signal and g of t is also a periodic signal, and both have the same time period. Listen carefully. F of t is a periodic signal, g of t is also a periodic signal. As these both signals are periodic with the same time period, then what is the cross correlation, which is r of f comma g of tau is equal to 1 by t integration over the minus t by 2 to t by 2 f of t into g of t minus tau dt. So if you see clearly, there is no need of limit here, and remaining everything is same because we are doing exactly over one time period here. That is the case here, and no need of any limit. But in this case, these are aperiodic signals, so we have to use the limit here. For these are the periodic signals, so don't need to use the limit, and remaining thing is same as it is. So for aperiodic signals, you have to use the limit, and for periodic signals, you don't have to use the limit. So now the next point is for periodic signals with different time period. Suppose f of t is a periodic signal with time period t1, and g of t is also periodic signal with time period t2. So both these time periods are different. So now we have to find the common time period. The common time period is LCM of the T1 and T2. The common time period T is the LCM of the T1 and T2. So now, so first thing is you have to find the common time period based on the T1 and T2. Then what is the cross correlation between the f and f of t and g of t, which is r f of t comma g of t of tau is equal to 1 by t integration over the minus t by 2 t by 2 f of t into g of t minus tau dt. This is same as this one. The only thing is we made the common time period. So here let me write this point so that you can easily able to understand. So here f of t has a time period of t1 and g of t has a time period of t2. These two are periodic signals but having the different time periods. So I have found the common time period with the help of LCM of T1 and T2. The capital T is nothing but it is a LCM of T1 and T2. So with the common time period, then we have with the cross correlation. So this is a point always you have to keep in your mind. So this is a thing always you have to keep in your mind. So now here, listen carefully. I can say for power signals, don't use convolution method to figure out correlation, but use integral method. So for power signals, don't use convolution method to figure out the correlation, but use integral method. So basically, this point always you have to keep in your mind. See, whereas for energy signals, I've already told you. For energy signals, I've already told you one important point. What is the thing I've already told you? Which is, I already told you for energy signals. So let me write this point. For energy signals, I've already told this important point, right? So this is nothing but f of t convolution of g of minus t and finally replace t by tau and tau by t. So this I've already told you, right? So this I already told you. So there, if you see in the energy signals, we have figured out some relation between the convolution as well as a correlation only for energy signals. But in this case, no. We are not going to find any relation between a correlation as well as a convolution because these are the power signals. So for power signals, don't use convolution method in order to figure out correlation, but we are going to use the integral method. So this point always you have to keep in mind. So in the case of energy signals, we have figured out the relation between the correlation as well as the convolution. But as in the case of power signals, we are not going to find any relation between the correlation convolution, but we are going to use the integral method. So for power signals, don't use convolution method to figure out correlation. Means you don't use the convolution method in order to figure out the correlation, but use the integral method. So for power signals, don't use the convolution method in order to figure out the correlation, but use the integral method. So here, what I am trying to tell you is very simple. See, in the case of power signals, don't use the correlation method in order to figure out the correlation, but instead of that, use the integral method. So now the next point is, suppose there is a function f1 of t. The f1 of t is nothing but a cos of omega naught t plus 5. So f1 of t, let me assume there is a function f1 of t which is equal to a cos of omega naught t plus 5. So definitely we can say this is a periodic signal, and f2 of t is equal to a sin omega naught t plus 5. So f2 of t is also periodic signal. Only thing is one is cos and the other is sin. Then if you want to find what is the autocorrelation of the f of 1 with respect to f of 1, then finally if you solve, then we are going to get. So basically these are the periodic signals. So definitely I have already told you all the periodic signals are the power signals. This point I have already told you. So therefore, as all the periodic signals are the power signals, so what is the autocorrelation? If you simplify, finally we are going to get the autocorrelation of the f1 with respect to tau is equal to a square by t cos of omega naught tau. So this is the relation you have to keep in your mind. Suppose if you find the autocorrelation between f2 and f2, then finally we are going to get a square by 2 cos omega naught tau. So for both these things, the formula is same. The autocorrelation is same, which is a square by 2 cos of omega naught tau. So this proof I already given in the signal and system course. But here I am going to discuss only the important concepts only I am going to discuss. So this one always you have to keep in your mind. So when f1 of t is equal to a cos omega naught t plus 5 and f2 of t is equal to a sin omega naught t plus 5, then the autocorrelation as these two signals are the periodic signals. So all the periodic signals are the power signals. So definitely the autocorrelation of either anyone definitely are going to get finally both are same, which is equal to a square by 2 into cos of omega naught tau. So this one always you have to keep in your mind. A square by 2 cos omega naught tau. So this formula you have to keep in your mind. So this formula always you have to keep in your mind. So basically, if the function is a cos omega naught t plus phi or a sin omega naught t plus phi, finally you are going to get the autocorrelation is equal to a square by 2 into cos omega naught tau. So this one always you have to keep in your mind. So let me go for the another function. Suppose f of t is equal to b into u of t. It is a unit step signal. For t less than 0, its value is equal to 0. And for t greater than or equal to 0, its value is equal to b. Then if you try to, definitely this is also power signal because the energy is equal to infinite and the power is equal to finite. So therefore definitely we can say that this is said to be basically a power signal. I've already told you f of t is equal to b into u of t. So what is the energy? Energy is equal to infinity and power is equal to finite. I think the power value is equal to b square by 2, I guess, but I forgot. But I guess the power value is equal to b square by 2, I guess, b square by 2. So I wanted to remember this one. Remember this one. So this point always you have to keep in your mind, right? So this is the formula, I guess. So energy is equal to infinite. Already energy is always equal to infinite for this one. So power is equal to b square by 2. Then we can say that so therefore what is the RF of tau, the autocorrelation? Definitely we can say the signal is said to be power signal. So as I can say the signal is said to be power signal, so definitely the autocorrelation is nothing but b square by 2 we are going to get. So autocorrelation of the function f with respect to f is nothing but b square by 2. So definitely you can say it is a constant value. So this one always you have to keep in your mind. So these two formulas always you have to keep in your mind. So when the function is a cos omega naught t plus phi or a sin omega naught t plus phi, the autocorrelation is nothing but a square by 2 cos omega naught tau. Suppose if the function f of t is equal to b into u of t, then the autocorrelation is equal to b square by 2. So now the next point is the autocorrelation of f and f at plus tau is equal to the autocorrelation of f and f at minus tau, both are equal. So it means that the autocorrelation of the function f with respect to f is always an even function or even signal. The autocorrelation of function f with respect to f is always an even signal. So this point always you have to keep in your mind. So therefore we can say the autocorrelation of the function f with respect to f is always an even signal. It is always an even signal. So this point always you have to keep in your mind. So therefore the autocorrelation of the function f with respect to f is always an even signal. So RFF of plus tau is equal to RF of minus tau. So this point I have already told you so many number of times. So this point you have to keep in your mind. Same thing is also this formula is also applicable for any signal as well as a power signal. This concept is same. So whatever this concept is applicable for both the energy signal as well as the power signal. So this point I have already told you in the case of energy signal also. Same concept is also going to hold in the case of the power signal also. So therefore you can say the autocorrelation. So always remember the autocorrelation is always an even function, whether the signal is an energy signal or whether the signal is a power signal. So this point I have already told you. So therefore we can say the autocorrelation is always an even function or even signal, because no matter whatever the signal, whether it is energy signal or power signal, always it is going to satisfy this property. So this is what I am trying to tell you. So now the next property is, which is the autocorrelation function at tau is maximum at tau is equal to 0. Maybe this value can be repeat at other tau value but not exceed this maximum value. So RFF of 0 is called as the power of the f of t. So listen carefully what I am trying to tell you. See what is the RFF of tau? If suppose if you draw the function, always you are going to get the maximum value at tau is equal to 0. This maximum value you can get even at the other distance also, but no other value can exceed this value. So this is always the maximum value. So RF of tau is a maximum value at a tau is equal to 0. Maybe this value can repeat at other tau value, but it is not going to exceed this maximum value. So RF of 0 is nothing but it is a power which is going to present in the f of t. So if you see clearly for this one, so let me go for this one. So for this function, suppose if I draw the autocorrelation, how we are going to get, suppose if I draw with respect to tau graph, so with respect to tau, so what I am going to get, it is a cos function, right? It is a cos function. Let me take another thing. So like this you are going to get a square by 2 into cos omega naught tau. So like this you are going to get, right? So like this waveform you are going to get. So what is the maximum value? The maximum value is a square by 2. A square by 2. So this maximum can occur at different instants. At tau is equal to 0 also it can occur, or at omega naught tau. At omega naught tau is equal to 2 pi also it is going to get occur. At omega naught tau is equal to 0. So at omega naught tau is equal to 4 pi also this maximum is going to get occur. So therefore we can say, at instant tau is equal to 0, we are going to get the maximum value. Maximum value. This may repeat at other instant also it is going to get repeated, but no other value will be more than this value. So this is always the maximum value. And this value is nothing but it is the power of the f of t. It is the power of the f of t. It is the power of the f of t. This maximum value is nothing but the power which is going to present in that function f of t. So for this signal, what is the power? The power is nothing but RMS value whole square. So what is the RMS value? A by root 2. So do the square of that one. So it is equal to a square by 2. So this is the same thing, right? So this maximum value itself is nothing but the power which is going to present in the signal. So therefore you can say clearly, I have already given the explanation also. So therefore we can say, whenever any periodic signal, if you are going to take it and if you are going to do the autocorrelation, and then at tau is equal to 0, you are going to get the maximum value. At other instant also, you are going to get this maximum value. But at no other instant, no value will be more than this. This is always the maximum value. But at tau is equal to 0, always you are going to get the power value. So it is always going to indicate the power which is going to present in this function f of t. So Rf of tau is equal to 0 is always going to tell you the amount of power which is going to present in a signal f of t. So this is what I am trying to tell you. So finally I can say the Rff of tau is always maximum at tau is equal to 0, and maybe this value can be repeated at other values of tau value, but it will not exceed more than this value. And Rff of tau is equal to 0 is nothing but the power which is going to present in a signal f of t. Then what is the next point is the Rff of tau. The Rff of tau is nothing but if you try to find the Fourier transform of this one, if you try to find the Fourier transform of this one, we are going to get power spectral density. For energy signal means energy spectral density. For power signal means power spectral density, which is equal to limit t tends to infinity mod of f of omega, mod f of omega whole square by t. This is a Fourier transform. This is a Fourier transform. Here I have kept that t here, small t here I have kept here. So what is the meaning of this one? Let me tell you. So here, if you do the Fourier transform of this one, we are going to get the power spectral density, which is equal to limit t tends to infinity mod f of omega with a base t whole square by capital T. So what is the meaning of this one? Let me tell you. So mod of f of omega with the base t is nothing but is a Fourier transform of the f of t signal only in the range of minus t by 2 to plus t by 2. Means only over the time period t only we have to find the Fourier transform. Whereas the whole range, in the case of energy signal, we have to find the mod of f of omega for all the range. But here we have to do only for one time period. Case from minus t by 2 to plus t by 2 only. So therefore, the magnitude of f of omega over the one time period with the base t is nothing but we have to do the Fourier transform of the signal f of t only in the period from minus t by 2 to plus t by 2. So these points always you have to keep in your mind. So now the next thing is, if f of t is a periodic with a period t, then if f of t is a periodic period t, then Rff of tau is also periodic with the same period t. So what I am trying to tell you, suppose if f of t is a periodic signal which is having a period t, and if you try to find the autocorrelation, it is also having the same time period t as it is. So this is what I am trying to tell you, because the frequency is same, right? So you can see clearly, we suppose this is a power, this is a signal, right? For this signal, this is autocorrelation. What is the frequency here? Omega naught. So here also frequency is omega naught. So as frequency is same, they both will have the same time period. So therefore, the time period will be same. So therefore, we can say if a function is a periodic signal which is having a time period t, then its autocorrelation will also be it will be also periodic with the same time period t. As I have clearly explained in the example also. So you can see clearly here. So this is a function, it's a periodic signal which is having a period of t. This is also a periodic signal which is having a time period of t, because the frequency is same in both the cases. So now the next point is, if a signal f of t, given a signal f of t, we can find the the autocorrelation of the function f. But with the given autocorrelation, we can't get the f of t uniquely. So this is what I'm trying to tell you. Suppose if you know f of t, suppose if they are given f of t, then you can get the autocorrelation. But if they given the autocorrelation, you cannot get back the f of t uniquely. So therefore we can say that if you know f of t, then you can get the autocorrelation. But if you know autocorrelation, we cannot get back the f of t in a unique manner. So therefore we can say this is not a unique pair. So what is the meaning of this one? See, as you can see clearly here in the example only. So these two functions, their nature is different, but still they have the same autocorrelation, as you can see clearly here. So as the two functions are different, but still the autocorrelation is same. Suppose if they are given the function f of t, then you can get the autocorrelation. But if they are given the autocorrelation, you cannot get back the signal uniquely, as you can see clearly from this example only. So these two functions have the same autocorrelation. So if they are given the autocorrelation, you cannot tell this belongs to which type of signal. So this is what I am trying to tell you. So therefore, if they are given the signal f of t, then we can figure out the autocorrelation. But if they are given the autocorrelation, we cannot figure out the signal f of t in a unique manner, because I have already given a beautiful example also. Because for a signal f of t is equal to a cos omega naught t plus phi, and the other signal a sin omega naught t plus phi. Both these signals have the same autocorrelation, which is a square by 2 into cos omega naught 2. So what is the meaning of this one? Even though signals are different, but still the autocorrelation is same. So therefore, if they are given the f of t, we can get the autocorrelation. But if they are given the autocorrelation, we cannot get back the signal in a unique manner. So this is the point always you have to keep in your mind. So now the next point is, if f of t is a power signal, then PSD, it tells power per frequency. So how much amount of power it is present per frequency, that we are going to know with the help of PSD. There, if f of t is energy signal, what is the meaning of ESD? Energy per frequency means the amount of energy is present per each frequency. Here it is a power signal. So PSD means it is going to tell you the amount of power which is going to present per frequency. So this is the point always you have to keep in your mind. So always remember, if f of t is energy signal, then ESD means it is going to tell you the amount of energy it is going to present per frequency. Suppose if f of t is a power signal, then PSD is going to tell you the amount of power which is going to present per frequency. So here, suppose if you want to find what is the power which is going to present in the signal f of t, which is equal to 1 by 2 pi integration over the omega is equal to minus f to plus m to power spectral density into d omega. So this point always you have to keep in your mind. So if you want to find what is the amount of power which is going to present in the signal f of t, the formula is, which is equal to 1 by 2 pi integration over the omega is equal to minus f to plus m to power spectral density into d omega. So this is a formula we have to remember. So therefore we can say that. If you want to find what is the amount of power which is going to present in the signal f of t, the formula is 1 by 2 pi integration over the omega is equal to minus f to plus m to power spectral density into d omega. So these things always you have to keep in your mind. Now the next point that we are going to discuss is here, power p is equal to limit t goes to infinity 1 by t into integration of minus t by 2 to t by 2 f of t whole square dt. This is for aperiodic signal. This one I have already told you. For aperiodic signal, what is expressed to the power p, which is equal to limit t goes to infinity 1 by t into integration over the minus t by 2 to t by 2 f of t, mod f of t or f of t. For real signal f of t, for complex signal mod f of t. So for mod f of t whole square dt, I have already told you, generally you can use mod f of t. Suppose mod f of t will be equal to f of t, but for real signals. Otherwise, just for a complex signal, how to figure out the magnitude, with the help of root over. Suppose if f of t is equal to a plus iv, then mod of f of t is equal to root over a square plus b square. So you know these things, right? So I don't need to further explain. So for a aperiodic signal of f of t, the power which is going to present here is equal to limit t dash to infinity 1 by 2 into integration over the minus t by the t by 2 mod f of t whole square dt. So now what I am going to for periodic signal. So for periodic signal, we are going to find only the power in only one period. Instead of trying to find the energy in each and every period and dividing by over the whole time period, instead of that, we will try to find energy only in one cycle and also period of one cycle only. Then we are going to get the power. So power is equal to energy by time. Energy is integration over the one time period f of 2 whole square dt by time period t. So therefore, we can write like this 1 by 2 into integration over the minus t by 2 f of 2 whole square dt. So therefore, I have already told you that power is equal to energy by time. So for a periodic signal, I will try to find only the energy in one cycle and I will take the time only for one cycle. So therefore, we can say integration over the one time period f of t whole square dt by time period t. So therefore, we can say 1 by t into integration over the minus t by 2 to plus t by 2 f of t whole square dt. So this expression always you have to keep in your mind. So therefore, the power P is equal to 1 by t into integration over the minus t by 2 to t by 2 f of t whole square dt. So this expression for the periodic signal, the power which is going to present in the periodic signal. Suppose if they are given the trigonometric series, suppose if they are given the trigonometric series in the trigonometric form. So listen carefully. For a periodic signal, they are given the Fourier series in the trigonometric form. Then what is the power we need to figure out? I've already told you Fourier series is going to applicable only for periodic signal, and all the periodic signals are power signals. Power signal means the energy is equal to infinite and power is equal to finite. So how to get the value, which is P is equal to a naught square plus sigma n is equal to 1 to infinity a n square by 2 plus b n square by 2. So this is the point you have to remember. So you know what is the trigonometric expression f of t is equal to a naught plus sigma n is equal to 1 to infinity a n cos n omega naught t plus b n sin n and omega naught t. I've already told you, right? So just find in the RMS value and do the sphere. Just find it for each and every component. Try to figure out the RMS value and do the sphere here. So listen carefully. Let me write here. So let me write the expression of the trigonometric Fourier series for a periodic signal a naught plus sigma n is equal to 1 to infinity a n cos n omega naught t plus b n sin n omega naught t. So this is the expression of the Fourier series for trigonometric Fourier series for periodic signal. So as all the periodic signals are power signals, so I want to find what is the power present in the signal f of t. So just do the summation of the RMS of the just do the summation of RMS value whole square. So for a naught, what is the RMS value? A naught n, because it's a DC signal, to the square of that one signal for a n. So sigma, keep saying sigma n is equal to 1 to infinity. So for this component, what is the RMS value? RMS value is a n by root 2. So but we have to do the square, right? Square plus for this value, what is the RMS value? Bn by root 2. So do the square, that's it. So this is the solution. So if you simplify, what we are going to get, the all power which is going to present in the signal is a naught square plus sigma n is equal to 1 to infinity a n square by 2 plus b n square by 2. So this formula always you have to keep in your mind. So always you have to keep in your mind. So therefore we can say the amount of power which is going to present in the signal f of t is equal to a naught square plus sigma n is equal to 1 to infinity a n square by 2 plus b n square by 2. So what I am trying to tell you, suppose there is a periodic signal. So periodic signal we are going to express in the format of the trigonometric form, in the format of the trigonometric Fourier series. So the power is nothing but for each and every component try to find the RMS value and do the square, that's it. So therefore finally you are going to get for this signal the RMS value is the DC value itself, and for such form the RMS value is equal by root 2. So do the square for each and every RMS value and do the summation, we are going to get the result. So power P is equal to a naught square plus sigma n is equal to 1 to infinity a n square by 2 plus b n square by 2. So this is the overall power which is going to present in this trigonometric periodic signal. Suppose if they are given the Fourier series in the exponential manner, if they are given in the exponential Fourier series, then how to figure out the power, which is sigma n is equal to minus 7 to plus root a mod of c of n whole square, mod of c of n whole square. So I already told you what is the expression of the Fourier series in the trigonometric form, in the exponential form. F of t is equal to sigma n is equal to minus infinity to plus infinity cn into e to the power of jn omega naught t. Right? So this is the expression. So this is the expression. So this is the expression of the Fourier series in the exponential format. So as it's a periodic signal, so we are going to calculate the power. So power is nothing but sigma. So sigma n is equal to minus infinity to plus infinity. Just take the magnitude of the Cn. I take the magnitude because it's a complex number, right? It's a complex number. Cn is nothing but it's a complex number. So it's a complex number, right? Cn is nothing but it's a complex number. So therefore, what I'm going to do here, I'm going to do the square of this one. I'm going to do the square of this one. See, if it is a simplification, what I'm going to get here, I can write like this also. Say n is equal to 0 to infinity, which is an square by 2 plus bn square by 2. As I already told you, right? See, basically, n is, see, I already told you, b0 is equal to 0, right? b0 is equal to 0. So if you substitute n is equal to 0, then what you are going to get? If you substitute n is equal to 0, we are going to get a0 square by 2 plus b0 square by 2, and this value is equal to 0. But there should be another thing, right? So therefore, what I am trying to do is simply, we can say, so we cannot write like this. So let me write this part, because it is going to come here. n square by 2 is coming, and we need only n square. So therefore, we cannot write like this. So this is what I am trying to tell you. So therefore, these expressions you have to keep in your mind. So these expressions always you have to keep in your mind. So therefore, we can say the only thing is mod of C of n whole square. So this is the expression of the power in the trigonometric format, and this is the expression of the power in the exponential format. So this is the thing always you have to keep in your mind. So this is the expression of the power in the trigonometric Fourier series, and this is the expression of the power in the exponential Fourier series. So what is the expression of the power in the trigonometric series? P is equal to n square plus sigma n is equal to 1 to infinity an square by 2 plus bn square by 2, and the expression of the power in the exponential Fourier series is P is equal to sigma n is equal to minus infinity plus infinity mod of C of n whole square. So these things always you have to keep in your mind. And I've already told you the other expression, r f comma f and tau is equal to 0. Here also you are going to get the value of the power, which is going to present in the signal f of t. So autocorrelation of the signal f of t, and then try to find that tau is equal to 0. What is the value? That value is nothing but the amount of power which is going to present in the signal. So it is the mean of the squares of the values of f of t. So mean of square values of f of t. So this is nothing but mean of square values of the f of t. So this is what I am trying to tell you. So finally, these are the different expressions of the power for a periodic signal, So these are all for periodic signals only. So this is for periodic signal. If the Fourier series is represented with trigonometric manner, if the Fourier series is represented in the exponential manner, so with the help of autocorrelation also you can figure out the power. So these are the different expressions you have to keep in your mind. So finally I can say, for a periodic signal, if you want to figure out the power is equal to limited to infinity 1 by 2 into interest over the minus 3 by 2 t by 2 f of t whole square dt. For periodic signal, if you want to find the power, it is equal to 1 by t interest over the minus 3 by 2 t by 2 f of t whole square dt. And for the periodic signal, if it is represented in a trigonometric format, then the power is a0 square plus sigma n is equal to 1 to infinity an square by 2 plus bn square by 2. If the Fourier series is represented in the exponential format, then the power present is sigma n is equal to minus 70 plus 2 plus 70 mod of C of n whole square. So with the help of autocorrelation also we can figure out the power, which is the autocorrelation of the function f of t with respect to f of t at tau is equal to 0. Find this value, and it is equal to the power which is going to present in the signal f of t. So basically it is equal to mean of the squares of the f of t. So these things always you have to keep in your mind. Suppose the next point is, suppose I have already told you, suppose y of omega is equal to f of omega into h of omega. So for LTI system I have already told you, for LTI system if the input is f of t, and if the impulse response is h of t, then the output is y of t. So y of t is nothing but y of t is equal to f of t convolution of h of t. So this is in the time domain. So I have already told you the convolution time domain, and it changes to the multiplication of Fourier transform in the frequency domain. So it will become y of omega is equal to f of omega into h of omega. So therefore we can say that the convolution in time domain leads to multiplication in frequency domain. So because of that, y of omega is equal to f of omega into h of omega. As I have already told you, the Fourier transform is approximately, it's a complex number by 3 and the phase angle. So I am going to transform in the magnitude part. So magnitude of y of omega is equal to magnitude of f of omega into magnitude of h of omega. So now I want to find what is the power which is going to present in the signal y of t. So I have already told you what is the formula. Just now we discussed, right? What is the formula here? It is 1 by 2 pi integration over the omega is equal to minus infinity to plus infinity power spectral density of y of t, power spectral density of y of t into d omega. So power spectral density of y of t is nothing but power spectral density of f of omega and power spectral density of h of omega. So these things always you have to keep in your mind. So here what I am trying to tell you is very simple. So actually what is expression is like this to be expression. Here let me write here what is the actual expression. Power is equal to, it will be like this one. So I have not written that part, so let me write it so that you can easily able to understand. So what is the power? Power is equal to, I am going to, as it is a periodic signal, I am going to assume time period is 2 pi. So 1 by t, right? 1 by t means t is equal to 2 pi. So integration over the time period. So in the frequency domain I am doing this. In the frequency domain I am going to do. So here, what is the thing we are going to get? So mod of y of omega whole square d omega. So this is the thing I am trying to tell you. So here mod of omega will be there. So here what is the thing? It will be the power present in the y of t is equal to 1 by 2 pi. So basically I am going to calculate the power in the frequency domain. In the frequency domain I am going to calculate. So I have already told you what is the power expression in the frequency domain. The frequency domain just now we have discussed, right? Either the energy or power, I have already told you. It is nothing but energy of power 1 by 2 pi integration over the omega is equal to minus infinity to plus infinity mod of y of omega whole square d omega. Either it is energy or power, the formula is same. So here we can say same thing, right? So same thing. So whether it is energy or power, the formula is same. The frequency domain. So P is equal to 1 by 2 pi integration over the omega is equal to minus infinity to plus infinity mod of y of omega whole square d omega. And mod of y omega is nothing but mod of f of omega into mod of h of omega and to the square a into b whole square is equal to a square b square. A into b whole square is equal to a square to b square. So from that we can say that it will become mod of f of omega whole square into mod of h of omega whole square. And mod of f of omega whole square is nothing but it is nothing but power spectral density. And here as it is an even function, all these are even functions, right? Mod of y of omega whole square is a even function. So because of that, instead of doing from omega is equal to minus to plus infinity, I will do only from omega is equal to plus infinity. So I multiply by 2. So 2 and 2 cancels. We are going to get 1 by pi integration over the omega is equal to 0 to plus infinity. Power spectral density of f of t into power spectral density of f of t is nothing but mod of y of omega whole square into mod of h of omega whole square into d omega. So this is what I am trying to tell you. Same thing here only. So what I have did basically, power and energy expression is same. Power is equal to 1 by 2 pi integration over the omega is equal to minus to plus infinity mod of y of omega whole square d omega. Mod of y of omega is nothing but mod of f of omega into mod of h of omega. So do the square. We are going to get mod of f of omega whole square into mod of h of omega whole square. So this power spectral density is the even function. So instead of doing from omega is equal to minus to plus infinity, I will do from 0 to infinity. So here I will keep here 2 to cancels here, going to get 1 by pi integration over the, so let me write here, it will become 1 by pi integration over the omega is equal to 0 to infinity mod of y of omega whole square d omega. And you know the value of mod of y of omega is nothing but mod of f of omega into mod of h of omega. This option will simplify. We are going to get this expression. So this is the expression that we are going to get. So mod of f of omega whole square is nothing but power spectral density in f of t. This is we can write power spectral density in h of t also we can write, but I have not written any of the concept is same. I think you have understood. So this is the expression that you always have to keep in your mind. And the power spectral density is always even function and real function. And what I told you, this power spectral density is always a even function and it is always a even also, is a real also. Always you are going to get only the real value you are going to get. So power spectral density is always a even function as well as a real. As the power of input increases, then the power in the output is also going to get increases to a finite value always. So as the input power increases, then the output power is also going to get increases to a finite value always. After that, it is going to become saturated. So what is the meaning of this one? So listen carefully. Suppose I am going to draw input and output. Suppose let me draw the input power and output power here, so that you can easily able to understand. So with respect to time. So this is the input power and this is the output power. So let me draw the graph here. Suppose input power is increasing. If the input power is increasing all the way, so output power will also increase, but after some time it will become saturation. Even though input power is increases, but still the output power is constant. So this is what I'm trying to tell you. So this person, see, as the input power increases, yes, the output power also increases after certain time. After that, it will become saturated. It will become saturated. Even the input power is increases, the output power will remain saturated. So this is what I'm trying to tell you. So therefore, we can say, as the power in the input increases, when the power in the output increases, a finite value always. I'm already told you. See, as the input power increases, the output power is also going to get increases. But after certain time, it will reach a saturation, means it will become a finite value. The next point is, power in response of any system need not necessarily be proportional to the input power of a signal. The power in response of any system need not necessarily be proportional to the input power of a signal. So what is the meaning of this one? Suppose what I am trying to tell you is very simple. Let me draw the graph here. Suppose you have taken some system. You have taken some system like LTI system. Here, see, I have already told you this is the input power and this is the output power. See, I have already shown you the graph, right? I have already shown you the graph. Here the input power is increases. Up to a certain time, it will take the time t1. So up to time t1. So what I can say, for t lies from 0 to t, the output power is directly proportional to input power. I can write like this. But at t greater than or equal to t1, the output power is equal to constant. It is independent. It is independent of the input power. So we can say, yes, after a certain time, it can depend on the input power, and after a certain time, it may be independent of the input power. So it is not necessarily always the output power is always proportional to input. It is always not necessary that the output power is always proportional to input. For a certain time, it may be proportional, but after a certain time, it may be constant. So what I am trying to tell you, we can see clearly from this picture, after a certain time, the output power is proportional to input power. But after a certain time, the output power is constant. The output power is constant, as you can see clearly from this picture. So therefore, we can say, after a certain time, the output power is proportional to input power. But after a certain time, the output power is equal to constant. So what is the meaning of this one? We can say, the output power can be proportional to input, or the output power may be independent of input. So this is the meaning of this one. Output power can be proportional to input, or the output power can be independent of input also. So after a certain time, the output power can be depending on input, and after a certain time, the output power can be independent of input also. So therefore, what is the meaning of this one? Finally, I can say that the output power in the response of any system need not necessarily to be proportional to input power of a signal. It can be depending or it can be independent. So we can say finally, after a certain time, the output power can be proportional to input power, and after a certain time, the output power may not be depending on the input power. So this is the meaning of this one. It is not always, need not be always depending on the input power. So output power need not be always depending on the input power. So finally, I can say, for a certain time, the input power is proportional to input, and after a certain time, the output power is independent of the input power. So this is what I am trying to tell you. So these concepts always you have to keep in your mind. So this is all about the cross correlation as well as the autocorrelation for the power signals. Now we are going to discuss the another concept which is called as the Laplace transform. So here, basically, the Laplace transform is going to apply for the time domain, and for the Z transform is applied for the discrete domain. So this is a point I am going to tell you early itself. So the Laplace transform is going to apply for the time domain, and for the Z transform is applied for the discrete domain. So this way I am going to tell you this concept early itself so that you can easily able to understand. So now listen carefully. Suppose for f of t, what is the Fourier transform? So for f of t, if you are going to do the Fourier transform, then what is the Fourier transform? I already told you, f of w is equal to integration from t is equal to minus into plus of t, f of t into e to the power of minus j omega t into dt. So this is called as a Fourier transform on the signal f of t. So this expression I have already told you. Suppose if integration of t is equal to minus infinity to plus infinity, mod of f of t dt is less than infinity. So what is the meaning of this one? If the signal f of t is absolutely integrable, absolutely integral means take the modulus of the f of t and then do the integration over the time from minus infinity to plus infinity. if you are going to get a finite value, then f of omega is well defined. Then it is well defined, means we can say it is defined for each and every value of the omega for range of minus infinity to plus infinity. This point I've already told you why it is like this, because if you take the overall magnitude, so if you take the overall magnitude, see what I am trying to tell you, see the magnitude of A into B is nothing but magnitude of A into magnitude of B. Here A is nothing but f of d and B is nothing but e to the power of minus j omega t. So then magnitude of f of t into e to the power of minus j omega t is nothing but magnitude of f of t into magnitude of e to the power of minus j omega t. And the magnitude of e to the power of minus j omega t is something but 1, because I've already told you the magnitude of e to the power of it, I theta is equal to 1. So based on this, what you are going to get happen here? The magnitude of f of t into e to the power of minus j omega t is something but which is equal to magnitude of f of t. So that is the reason I have kept here magnitude of f of t. So what is the meaning of this one? If the magnitude of the f of t means try to figure out the magnitude, or you can say the absolute value, or we can say try to find the magnitude of f of t, or we can say the modulus of f of t, and then do the integration over the minus m to plus of d. If you are going to get a finite value, then definitely we can say that the f of omega is defined for each and every value of omega, means the omega is lie from minus m to plus infinity. See, what is the meaning of this one? This we can also see, if this is going to give you a finite value, then that this part also going to give you the absolute value, right? So then this value is also going to give you the finite value. If the modulus value is going to give you finite value, then the scale of this modulus also going to give you finite value. So therefore, this is nothing but energy. So energy, finite energy is especially something but finite energy. So in simple words, I can say only one thing. If a signal, so listen carefully, if a signal is an energy signal, listen carefully, if a signal is an energy signal, then by default that the Fourier transform is well defined, means it is defined for each and every value of the omega. Suppose if the signal is not an energy signal, then we can say yes, f of omega is going to get exist, but for some values of omega, it is not going to get defined. So this is what I am trying to tell you. So listen carefully. Finally, suppose if a given signal is an energy signal, then f of omega is defined for each and every value of the omega from minus m to plus infinity. Suppose if a given signal is not an energy signal, then we can say that the further signal f of omega is going to get exist, but for certain values of omega it is undefined. Undefined means its value is going tends to infinity. So this point I've already told you so many number of times. So these things always you have to keep in your mind. So then the next point is, so what is the next point here? The next point is, listen carefully. Here f of t, for f of t, what is the Laplace transform? So we have learned about the Fourier transform, right? So now I want to tell you what is a Laplace transform. See, Laplace transform is nothing but wherever j omega is there, just replace j omega by yes, that's it. So if you apply the Laplace transform, f of t will change to f of which is equal to integration of t is equal to minus m to plus infinity f of t into e to the power of minus st into dt. So I've already told you this formula, right? This formula. So this is a Laplace domain. So this is a Laplace domain. If you want to Fourier transform is in place of yes, if you substitute j omega, we are going to get the Fourier transform. So now in S is nothing but S is equal to actually S value is nothing but sigma plus j omega, because it has a real part and imaginary part. So then what is the ROC? ROC is nothing but we say the real part of S. So the ROC is nothing but here the real part of S, which is called as the sigma in the case of Laplace domain. So I want to tell you only one thing. See, the Fourier transform is one of the special case of the Laplace domain, because here when S is equal to j omega means sigma is equal to 0, then the Fourier transform is going to get occur. So what is the meaning of that one? Fourier transform is one of the special case of the Laplace domain. So when S is equal to j omega, then the Laplace transform is going to change to Fourier transform. So this is a thing I am trying to tell you. So therefore, when S is equal to sigma plus j omega, then ROC is nothing but the real part of S, which is nothing but sigma. Then here, if integration of t is equal to minus infinity to plus infinity, so in place of S I have substitute. So listen carefully. What is the expression here? Let me do simplification so that you can able to understand. So integration of t is equal to minus infinity to plus infinity f of t into e to the power of minus st into dt. So here s is something but sigma plus j omega. So in place of s I am going to write the sigma plus j omega. Then finally what I am going to get, integration of t is equal to minus infinity, t is equal to plus infinity, f of t into e to the power of minus sigma t into e to the power of minus j omega t into dt. So if you try to find the magnitude value, so if you try to find the overall magnitude, then this magnitude is something but the magnitude of e to the power of minus j omega t is something but it is equal to 1. So this I am going to assume A and this I am going to assume B. So I already told you the magnitude of A into B is equal to magnitude of A into magnitude of B. As magnitude of B is something that it is equal to magnitude of e to the power of minus j omega t, its value is equal to 1. So therefore we are going to get only A value we are going to get, which is nothing but magnitude of f of t into e to the power of minus sigma t. So therefore integration from t is equal to minus infinity to plus infinity mod of f of t into e to the power of minus sigma t dt. If this value is less than infinity, then only we can say that the Laplace transform is going to get exist. So you can say when the if integration of t is equal to minus 70 plus 70 mod of f of t into e to the power of minus sigma t, if this value is going to give you a finite value, then only we can say the f of s is well defined. It is going to exist for some particular range of sigma. So you can see that what is the meaning of this one. So integration of t is equal to minus 70 plus 70 because the modulus of f of t into the power of minus sigma t, if it is less than infinity, then f of s is well defined. It is going to exist for some particular range of sigma. That particular range of sigma is called as the ROC. That particular range of sigma is called as the ROC. So therefore, we can say that what is the meaning of Laplace transform when f of t, if you apply the Laplace transform, we are going to get f of s, which is equal to integration of t is equal to minus 70 plus 70 f of t into e to the power of minus st into dt, where s is equal to sigma plus j omega. ROC is nothing but this is the real part of s, which is equal to sigma. So if the integration of t is equal to minus 70 plus 70 mod of f of t into e to the power of minus sigma t, if this value we are going to get less than infinity, then only that f of s is going to get well defined for some particular range of sigma, that is called as the ROC. So this is a point always you have to keep in mind. So therefore, what I am trying to tell you, suppose if I am going to compare the Fourier transform and the Laplace transform. In the case of Fourier transform, if the signal is said to be energy signal, then definitely we can say that the signal is having a well-defined Fourier transform is for each and every value of omega, we are going to get a finite value of f of w. Suppose if a given signal is not an energy signal, still the Fourier transform is going to exist, but the only condition is for some values of for some values of omega, the function is not defined, which is we are going to get an infinite value. In the case of Laplace domain, if the integration of t is equal to minus 70 plus infinity mod of f of t into the power of minus sigma t, if it is going to give you a finite value, then only the f of s is going to get well defined for some range of sigma, that is called as the ROC. For some particular range of sigma, that is called as the ROC. So now, if I am going to compare the Fourier transform or Laplace transform, then the Fourier transform is one of the special case of the Laplace transform and sigma is equal to 0. So therefore we can say that f of omega is equal to f of s when s is equal to j omega, means sigma is equal to 0. So in the case of Laplace transform, if you substitute s is equal to j omega, then we are going to get the Fourier transform. So therefore Fourier transform is the special case of the Laplace transform. So this is what I am trying to tell you. So therefore we can say when s is equal to j omega, so when s is equal to j omega means sigma is equal to 0, means on the imaginary axis, then we are going to get the Fourier transform. So therefore the Fourier transform is a special case of the Laplace transform. So in the case of Laplace transform, if you substitute s is equal to j omega, means sigma is equal to 0, means it is on the imaginary axis, then we are going to get the Fourier transform. So therefore we can say that the Fourier transform is the special case of the Laplace transform. So these points always you have to keep in your mind.